Assalamualaikum warahmatullahi wabarakatuh and a very good morning to everyone. So my name is Prof. Sharifah and today we'll be conducting the Renkei Control Feasibility Analysis during Energy Audit Workshop. Yeah. So I think we can start now and I believe the others will be trickling in. Yeah. So allow me to share my slide. Okay, so thank you again, everyone, for coming. So the title of the workshop today is the two-day workshop on Renkei Control Feasibility Analysis during Energy Audit. So this workshop is organized by the RTUN Consortium, which consists of the Process System Engineering Research Centre from University Technology Malaysia, JETA, De La Salle University, as well as the Waseda University. This workshop is in collaboration with Malaysia Association of Registered Electrical Energy Manager, as well as Optimal System Engineering. So for your information, RTUN is a consortium which aims to do real-time utility network energy efficiency optimization with Renkei. Yeah, so it's a consortium which Renkei Control was introduced by JETA, and this project is basically funded by ONSIT, JICA, and is an on-site research and education grant for the university consortium. So these are the RTUN consortium members who has been helping out to develop all these modules that we aim to disseminate all over ASEAN. So a bit about the workshop highlights. Basically, what we'll be covering today is we'll be introducing about what is Renkei control, yeah, and how Renkei control can help to minimize the energy consumption via energy digitalization. Yeah, and we'll be also talking about how, for example, if you're energy manager or if you're energy auditor, or if, for example, you want to analyze the potential of Renkei control inside your own company, for example, yeah. So you can, in this workshop, we aim to bring some knowledge to you on how you can use to evaluate, yeah, either your or your client energy systems, whether it have potential to use Renkei control, and what would be the possible energy savings. Yeah, so we will not be able to cover all types of equipments, but we'll be giving some examples on, for example, boiler and turbine system, as well as air compressor system in more details. And the others will be just introducing the assessment form, which you can use to do some preliminary feasible calculation if your system have potential for Renkei control or not. Yeah. We'll be introducing also about P-graph. Yeah. So what is P-graph? A P-graph is a process network synthesis tool to analyze the Renkei control energy saving potential. Yeah. So for example, when you want to do the energy saving calculations, the calculation is very complex. It requires, for example, if you're not a mathematician or mathematical modeler, it's going to be very hard for you to do all the calculations. Yeah. So using P-graph is a simple mathematical model tool which you require very minimal knowledge on mathematical model, but you can do various configuration. For example, let's say you have 5 boilers, maybe some plants have 6 boilers, and then all your boilers have different configuration going through all the steam headers and so on. Yeah. So the beauty of P-graph is that you can change, yeah, the number of boilers, the number of turbines, the different configuration going to the headers, and you don't have to create mathematical equation for each of it. Yeah. So we're going to introduce all of you to P-graph, which is a very powerful mathematical model tools, which is more towards visualization. And even though you have very minimal knowledge on mathematical modeling, you can use it to analyze your plant or your client's energy system, energy saving using Renkei control. Yeah. And finally, we will provide with a free hands-on tools on Renkei control assessment. So what is this Renkei control assessment tool? Basically, this tool, you can use it. Yeah, you can fill up all the information. The information is very minimal, but based on those information, it can give you a preliminary idea whether Renkei control have potential or no potential for your company. Yeah. So first of all, you can use this Renkei control assessment tool to pre-assess the feasibility of Renkei control. And if later, for example, there is high potential of Renkei control, you can use the tools that the other calculations that we have provided, like P-graph and so on, for you to do a more detailed calculation. And if you want a more detailed calculation again after that, then you can also contact us for us to do a more thorough analysis on your company or your client's company. Yeah. So who are the target participants of this workshop? We are targeting energy auditors, energy managers, or person in charge of energy system in the company. Also energy service companies, ESCO, and lecturers. Yeah. So basically, we would like to have someone who have some background in managing their utilities, or who have background in analyzing energy consumption for the industries, because the things that we'll be covering today is quite technical. It's not awareness level. So that's the reason we need someone that already have some preliminary background or preliminary knowledge on, for example, what are chiller system, how does it work, and so on, in order for you to understand. But of course, we'll be giving some fundamentals. It's just that all the calculations may be quite detailed if you are just someone without the technical background of energy system. Yeah. Right. So as have been mentioned in the registration form, when all of you have filled out previously, because this workshop is basically sponsored by ONSIT, and it's basically as an output of the research grant that we received from onsit.net. Yeah. So because this workshop was developed because of this research and education grant for University Consortium, so we need to do some study even after the completion of the workshop. So because of that, we hope and we require that all participants of this workshop, you can help us to, after the completion of this 2 days workshop, help us to fill in the post-workshop survey questions, which is just after the completion of this 2 days training. And then we require a feedback for you after 1 year, and then also after 2 years. Yeah. So what is the reason we require this survey form to be filled up to 2 years? Is because we want to know, for example, are the knowledge given in this workshop useful for you? Have you implemented it? Have you tried it out for your own company or your client? Do you think that the workshop is helpful? Yeah, so that is the reason why we need to know after 1 year and then after 2 years whether this workshop have helped you in some ways or not. Yeah, so it's going to be a very short and simple survey. So please don't worry, all the information in the post-workshop will be kept confidential. Only the analysis result, yeah, we may publish for ONSIT and others, but the detailed information like your company and everything will be kept confidential. Yeah. So just to introduce who will be the speaker of the workshop today. Me, myself, I'll be doing the introduction and the closing. Mr. Mike Suzuki, as well as me, Lee Pyo Ying, are from JETA, yeah, Japan Electronics Information Technology Association, yeah, and they are also from Asbil Corporation, and they are basically the Renkei control expert for this workshop. Yeah, so together with us also, we have Hong An, Siti Noor Azrin, and Dr. Fakroni, who are all from University Technology Malaysia, and they will be also be sharing about the tools that have been developed throughout the Artune Consortium workshop. Yeah. Right. So these are the tentative program. Yeah. So this is what we'll be doing. So now we are here, introduction to our Tune webinar. So after this introduction, Mr. Mike will be introducing about what is Renkei control. So he'll be providing you the information, what is Renkei control, where is it used, yeah, what is the benefit of it, and so on. And then from there, we'll go directly to uh, how to implement the Renkei control for various utility plant system. Yeah? So for example, the boiler and turbine generation system, BTG system. So Ms. Lee will be talking about the fundamental concept of how Renkei control can be applied for the BTG system. And then after that, Azrin will be introducing about the assessment tool, yeah, that you can use to assess if, for example, you have a boiler plant or you have a boiler and turbine plant, how you can assess your Renkei control feasibility. Yeah. So once Azrin has already explained how you can use the assessment tool to assess your boiler or the boiler and turbine generation system. Next, Dr. Fakroni and Hong An would be explaining how to do a more detailed calculation on how do you know what would be the energy saving. Yeah, so let's say you are a plant, so you have this boiler configuration data and so on. So how do you calculate what is the saving? Yeah, and then from the saving you can decide whether you want to implement it or not. Yeah, and you can also calculate your payback period and so on. Okay, so so basically from 12 until 5 p.m. today, we'll just be focusing on the boiler and turbine system, from what data to be collected, how do you do the calculations, how do you use pgraph, what is pgraph, how to use that software, and you have also hands-on application on using pgraph. Yeah, so we'll be doing some hands-on calculation using Excel and also using pgraph software. So I hope all of you have managed to download the pgraph studio software. Yeah. So for tomorrow, we'll be covering another 2 equipment. So basically what we are covering are the common utility equipment which most buildings or most industries have, which is the boiler, air compressor and chiller system. So for tomorrow, we'll be covering about air compressor system, how Renkei control can be applied for air compressor system, followed by followed by how to use the assessment tool to analyze the feasibility of your air compressor system. And then from there, we'll go again to some detailed demonstration on how to do the savings calculation for your Renkei control system. Yeah. And finally, the third module will be in the afternoon of tomorrow. We'll be going into the chiller system application for Renkei control, followed by the assessment tool. But we'll not be going through the calculation for energy savings for chiller because it'd be too long. Yeah, so we'll be only covering the detailed calculation of energy saving calculation for boiler as well as air compressor system. Yeah, and finally, we have a closing and way forward. Okay, so for those of you that are new to WebEx, let me just explain how to use WebEx. Yeah, so WebEx is this conference platform that you are opening now. Okay, so for your information, this is the mute or unmute button. Yeah, so some of you, when you join, maybe you forgot to unmute your mic. Yeah, so you can mute your mic here, and we would appreciate if you can mute your mic throughout the workshop, unless if you need to ask any questions. Yeah, so that we don't disturb any of the speakers when they are presenting. Yeah. And the next one is, for example, if you would like to switch on your camera, so you can press the start video to switch on or off your camera. And this one is, let's say, for example, you have problem with your Excel calculation or maybe with your pgraph studio calculation. You can, for example, share your screen by clicking here at the share button. Yeah. And finally, if you would like to ask any questions to the panels, yeah, to the speakers, so you can also use this raise up hand function. You can raise up your hand, and then when it's the Q&A time, we'll be calling your name. Either you can ask directly, or you can also use the chat. You can also write down your question in the chat box. Yeah, so there are 2 ways for you to ask question. One is you can write your question in the chat section, yeah, where you can click here and then the chat box will come out and you can type your question there. The second one is if you would like to talk directly to the speaker, please use the raise up hand function and we'll call you up during the Q&A session. Yeah, so this one is the exit button if you would like to exit from the WebEx anytime. Yeah. So a few notes to everyone. First of all, as I mentioned previously, please mute your mic during all the presentations so that we'll have a clear presentation by everyone. Secondly, some of you may require the Malaysia Energy Commission ST-CPD point. Yeah, so we are still applying for this ST-CPD point and we are still waiting for the approval. But let's say if the ST-CPD is approved, then we can also provide you with this ST-CPD point. Yeah, so it's still subject to approval. So if you, just in case we get this, so if you would like to get these STCPD points, since this is an online workshop, we require the participant that would like to get this STCPD point to switch on your video camera throughout the 2 days workshop. Yeah, because sometimes the Energy Commission, they will come in during the workshop, and then they will just scan through, yeah, if the people are switching on their camera or not. Yeah. Finally, next one is, as I have mentioned, please ask question in chat or use the raise hand function, and you can unmute your mic to ask your question. And please attend all the 2 day session, so that we will have a attendance form for the morning as well as the afternoon session for the 2 days. Yeah. So if you would like to get the e-cert, we require you to fill in the 4 attendance form. Would be 1 in the morning of today, 1 in the afternoon, and then another 2 for tomorrow, as well as the post-survey workshop after the completion of the workshop. Yeah. So if you complete 4 and 5, we'll be providing you the participation's e-certificate within 2 weeks' time. Yeah. And finally, for those that require the STCPD, if it's approved, it will be a different certificate that we will be provided, but it will be after the approval of the STCPD points by ST. Yeah. Okay, so here you can, if you click the button here just now, basically this is where the list of participants you can see, and this is where you can ask your questions. Yeah. All right, just as a reminder, as I have sent already in your email, we require you to download the PGraph Studio before the PGraph working session. Yeah. So how do you download PGraph? Basically, this is the link. Yeah. So I have also emailed this. It's http://pgraph.org PGraph Studio. I'll copy paste this in the chat also later if you have not installed it. And you should be installing the latest version, which is version 5.2.5.0. Yeah, so if you have problem with the installation, you can write in the chat, and we'll try to guide you through the installation process as well in the chat box. Okay. And for the workshop notes, you can download all the PowerPoint materials. Basically, we'll be giving all the PDF notes inside this one, and all the working sessions and the PGraph files are also available in this Google Drive. Yeah. So we'll also be pasting this link later on in the chat, and you can download all the required slide notes and everything from this link. Yeah. And finally, before we start our workshop today, so I would like to take a photo session with everyone. So if, for example, you guys can go to this workshop notes link. So let me just copy this workshop links. Okay. So I'll send these workshop links in the chat in a moment. Yeah. So basically, there's a virtual background available in this Google Drive. So we would appreciate if everyone can download that virtual background in the Google Drive. And basically, how do you change your virtual background? At the start video, there's an arrow here. You can click on it, and then you can click on the change virtual background. From there, there is a plus button here, which you can press, and then you can upload the virtual background picture, which you can download from the Google Drive just now, and then you just click the apply button. Yeah. So I would appreciate if we can take a photo session, first of all, while everyone is still fresh today, and then just in case not everyone will be here by 4:30 tomorrow. Yeah. So please, everyone, can you help download the virtual background first from the Google Drive? And then please switch on your video camera, and we would like to take a photo session of everyone before we start the Renkei control introduction by Mr. Mike. Okay. So I have put in the chat the link to the workshop material. You can click on the Google Drive. Okay. And then you'll find the virtual background available in that Google Drive. So you can try to change your virtual background and please switch on your camera and we'll be taking a photo session once everyone is ready. Yes, so can everyone switch on your video camera and then you can download the virtual background from the workshop training material Google Drive available in the chat. Okay, so I think some of you may not be able to change. Maybe you're using maybe you're using mobile or something. So I think we'll take the picture now, right? So I'll take the picture of the first one first. Okay, so please everyone switch on your camera. Okay, smile everyone. Second page, smile. Okay, so I think we only have those that switch on the camera. So I would like to thank everyone. So we're going to start our presentation session now. So for those that are applying for STCPD point, as I have mentioned, please switch on your video camera throughout the training. For those that are not applying STCPD, you can switch off your video camera or you can switch on. It's up to you. All right. So so now I would like to invite Mr. Mike, if you are ready, for the
Thank you
first
very much.
introduction of Renkei.
Thank you
Over
very
to
much
you, Mr.
for.
Mike.
Yeah, can you hear me?
Yeah, we can.
Okay, thank you very much, Professor Sharifa, for my introduction. And let me sharing my material first. Can you see my material, Introduction to Renkei Control?
Yeah, we can.
Okay, so thank you very much for your time. My name is Mike Suzuki, and I'm working for the Asbury Corporation Japan. And also, I'm a member of the JATA. And in JATA, we have the Renkei Control Working Group. This working group is trying to define the definition of the Renkei Control. From now on, I am trying to explain. And then we are trying to disseminate this very effective like a CO2 emission reduction like strategy and the control by control to like a Japanese industry or Japanese building sector. And also now we are trying to disseminate, promote this CO2 emission reduction like a method to like a Southeast Asia. And then this year, from the last year, we are collaborating with Professor Sarifar under the like Altune activity. Okay, let me start my presentation. So this is my content today. Firstly, just we will look at some interesting data about GHG abatement cost for selected major. And then after explanation about what is Renkei control, and also step 4 Renkei control project, and the typical Renkei control strategy for the energy saving, and also some example for the application and the scalability of the Renkei control. Then the last one is a summary of the Renkei control. Okay. So this figure, so this page is showing like a GHG abatement cost for the selected major, and this the figure provided by IEA, and this is about GHG abatement cost for selected majors, and GHG abatement cost is a cost or saving associated with reducing a greenhouse gas emission by 1 ton of the carbon dioxide. So basically, if this abatement cost number is the positive value, it means the major would cost money to reduce the emission. So if the negative, this abatement cost is negative value, it means the major reduce emission while also saving the money. So for the company who want to reduce GHG emission, so negative value is good. So basically, the maybe first the needs to considering about the investment cost, and also like operation cost for this like a new strategy like a renewable energy or like a Renkei control for the implementation. What's the size of the investment and what is the like operational cost? That will be like a cost part, and then the minus the fuel saving cost, and also there's like a depreciation like a period. So if this facility, this depreciation period is let's say 5 years, 10 years, so you can multiply the like a reduction cost to by reduction cost multiply depreciation period, and then so you can divide this number like the investment cost minus like energy saving divided by like a CO2 emission reduction, and this CO2 emission reduction is during the, like a depreciation period. So if this number becoming like a positive, that means there is a CO2 saving, but for the like profit and cost wise, that will be not so attractive. But in case of this number becoming a negative, not only to reduce like a CO2 emission, and also there is a saving, good saving from like let's say like fuel cost. So when we think about like a GHG reduction, first thing in our head is like a renewable energy, and from this figure, we can see like a renewable energy such as hydropower and wind power and the solar PV. So the average implementation of renewable energy bring in a positive abatement cost. So CO2 emission reduction good, but difficult to have like a payback. So on the other hand, the industrial energy efficiency has a wider range of abatement cost depending on the project, but however, in average, abatement cost is negative value. So this means we are reducing emission while saving the money. So other than the renewable energy, or other than advanced or efficient like the equipment, like improve energy efficiency by control and operation would be a good option for all high energy demand industry. So improving the efficiency of a process can be approached in several ways, but each method comes with its own set of advantage and limitation. So the first approach is replacing the existing equipment with new high efficiency equipment. So the advantage will be a new equipment will offer the high operation efficiency due to technological advancement. So it can lead to energy saving and potentially reduce the maintenance cost. But the the disadvantage or limitation is a high initial capital cost, and installation can be time consuming from the planning and also feasibility study and the procurement, installation and commissioning, and may disrupt ongoing operation. And only provide partial optimization as it does not account for the complex interaction between different process components. And this a second method is hiring experienced operator. So advantage will be a skilled operator can make the good decision making based on their knowledge and experience. And then basically it may be possible to improve the efficiency. But the limitation is there is no standard approach. The efficiency largely depending on the individual operator expertise. And it can be challenging for the operator side to considering all trade-off in a large and a complex plant environment to provide finely tuned and optimized operation. So to address these challenges and improve efficiency more effectively, a better solution is necessary. So this solution should be comprehensive, cost-effective, and easy to implement, and capable of optimizing the entire process by considering all trade-off and interaction and constraint. And one such solution is the implementation of the Renkei control. So Renkei control is orchestrating all the equipment to improve total efficiency. So next one is what is Renkei control. So let's look at the Renkei control. Renkei control is like a software approach, and the Renkei control is a control strategy designed to enhance energy efficiency in industrial sector and the building sector. And this approach is without the need for significant capital investment or major renovation to existing facility. So Renkei control utilizes software optimization technology to improve energy performance by coordinating and optimizing the operation of the various pieces of equipment and system. So the main purpose of Renkei control is to solve management issue for the plant to operation. For example, Renkei control address customer management concern, such as an environmental problem by reducing the carbon emission or maximizing production in an energy efficient way. So this will lead to achieve significant energy saving, leading to the reduction operation cost. So to achieve Renkei control, we should identify the boundary which the Renkei control should taking care of total optimization in the design scope. So typically the boundary could be the utility plant, like an individual utility plant, or like a linkage of the all like a utility plant by like a header. And also it is possible to expand the boundary for the optimization to include a manufacturing side as well. So Renkei control offer opportunity for the performance improvement by optimizing existing asset and infrastructure, and avoiding the need for the costly and disruptive upgrade or new equipment installation. So this is like a utility plant, and the fuel oil coming in or liquefied natural gas coming in, or may have some kind of like electric purchase. And in the utility plant, you may have some kind of like a compressor or a pumping system, or like a steam turbine, or a chiller system, or air compressor. And you may have like maybe 3 different like air compressor system, and that may like no connection in between, or you may have some kind of a connection. So you can define the boundary of the like optimization. So in any case, you need to provide the certain amount of like a utility to the manufacturing process side. And but to provide the certain amount of like a utility, uh, you, it is if you have like a multiple like a utility equipment, there is so many way for the operation. So depending on the operation, the energy consumption are different. So we are trying to minimize the usage of the like fuel or natural gas or like electric from outside. So if we want to reduce like CO2 emission, so we will calculate like the CO2 emission from the fuel oil or liquefied natural gas or like electric purchase from outside. Then we are trying to minimize like a total CO2 emission by this utility plant. Or you can just focusing on the manufacturing process side, or you can focusing on utility plus like a manufacturing process side. So basically, the utility plant provide the excess utility normally, because manufacturing process never allow like a shortage of the utility. So for the for the safety, the utility plant to provide like surplus utility, and then sometime like bypass, or sometime the just becoming like a waste. So the if we can provide the right amount of the utility the right time, that will be also will be like a saving. So this is the like important part compared with like how they approach. So this Renkei like optimization software approach is so short, very short construction period, around like 6 months to like 1 year. And if you compare with the like hardware investment, this is very less investment. So that means like high cost effective like investment. So we say quick win approach or low hanging fruit, and will contribute like a GHG emission reduction. So let's look at the like some like example for the Renkei control. And so in this diagram, there is the gas turbine and also waste heat boiler, and also like a gas boiler. And this is like electric chiller, and this is absorption chiller, and this is like a thermal storage tank. And this side is like a demand side, and demand side is requesting like a power for lightning, and also demand side is requesting like a chilled water for the air conditioning, and also the factory side is requesting like steam. So this utility, so in case the boundary for this utility is the turbine boiler, turbine, no, turbo chiller, and absorption chiller, and thermal storage tank. And then this boundary needs to provide certain amount of the utility to the demand side, and this utility side cannot control the size of the demand. Demand will be decided by demand side. And then they are, in this example, they are buying the electric from outside. So not only for the self-generation of the electric, also buying the electric from outside, and also needs to buy the natural gas from outside. And then normally, this is like before implementation of the Renkei control. So the skilled operator needs to make a decision for the operation of the gas turbine. For example, like a balancing between like a purchase electric and also like gas turbine load or number of the gas turbine. Also to provide like a chilled water needs to considering about which type of chiller should be used and what about like a combination between turbo chiller and absorption chiller. Also, you need to think about the balancing between like a steam production from the waste heat boiler and also additional like gas boiler, and needs to have a steam balance between absorption chiller steam consumption plus like steam demand. So, so, so operator needs to think about which turbo chiller should be used, which absorption chiller should be used, and how much do I use, better to use, like a discharging from the summer storage tank or like a charging into the summer storage tank. So there is so many way of the operation to meet the demand from the customer side. But the normally the company target is like minimizing the cost, maximizing the profit, and also maybe the recently also we are considering about environment, so it needs to considering about CO2 emission reduction. So under the consideration of the cost minimization, profit maximization, also the best effort for the CO2 emission reduction, operation side needs to considering about the operation for this facility. Also, this
ได้ยิน
facility
แล้วครับ
has like
ได้ยินละได้ยินละครับผมฮัลโหลเรียบร้อยแล้วเนาะครับ
like and also so this facility always having efficiency can be different between the maintenance and the maintenance. Also, some equipment may have the affection from the like weather side, like the humidity or like outside temperature. So there is so many things to think about to minimize the cost or the reduce like CO2 emission. So the Renkei control. So this is the the Renkei control approach. Renkei control can be added on top of the like existing control system. So the before the implementation of the Renkei control, of course, there is existing control system. So this existing control system, through this existing control system, the operation side can operate this facility. And also, of course, there's like a basic control loop in here. But the operation side needs to decide like a start, stop, or needs to provide like a set point. For example, like how much do I want to discharge from the thermal storage tank? Or what about the load of the turbo chiller? And or what about the load of the gas turbine? Or which boiler should I use? So after Renkei control, so Renkei control has like a software and optimization software. And in this Renkei control, you can specify objective function. So let's say the objective function is a cost minimization. So in this case, the Renkei control, the considering about cost from the purchased electric and the cost from the purchased natural gas. Then trying to minimize this total cost, but still needs to satisfy the like demand from the customer side. So then after, so this Renkei control will download, yes, download the optimal set point into existing control system. So the existing control system, basic control still the same. So, but before Renkei control, operation side needs to specify the set point for the each like a basic control loop. But instead of the operation team, this Renkei control server will download the directory for the set point into the existing control loop. Then provide the like optimal like a gas turbine load or like optimal like a boiler load or optimal number of the chiller or optimal load setting for the chiller or optimal amount of like charge and discharge amount from the thermal storage tank. So then overall efficiency improve and energy consumption and CO2 emission reduce. And also this will be a reduce the burden of the operation team. This is the concept of the like Renkei control. So to realize this Renkei control, so to implement Renkei control, various measurement and the control vendor apply their priority technology, their technology and optimize to the target system. So basically, this is the inside of the like Renkei control. We implementing. This is the software inside the software. This is a plan, and this is the existing control system. So we have interface in between the Renkei control and existing control system. So the easiest way is to utilize like OPC protocol. So nowadays the almost all like SCADA system or DCS system providing like OPC server. So it is very easy to connect. And then we have like a database. And then typically in case of the Renkei control server have like a plant model and also operation information and also optimization calculation and also energy management system. So for example, in this like a plant model, so I think during this Archon 2 days workshop, there is like a hands-on training to calculate equipment like efficiency. So equipment like a boiler efficiency or chiller efficiency or air compressor efficiency, we are part of the plant model. So we need to build like a equipment efficiency model because this is like a comparison. We better to use like a high efficiency like equipment. And also sometimes it may be necessary to have like a demand prediction model, especially if the plant has some kind of like storage, let's say like a battery or summer storage tank, that will be like a storage for the utility. So if the company has such kind of like storage, the demand prediction is will giving the company some profit if we can find like optimal usage of the capacity of the storage. And also we need to have like a process model, like a utility plant model, like an electric balance model or like a steam balance model or like a heat balance or mass balance. And then to build this plant model, we can use like a history data from the plant site, or sometimes it is quite difficult to having like a good correlation from the plant operation data. In this case, we refer like equipment specification from the vendor. Then we adjust this specification from the vendor to fit into the like actual operation. And also before the optimization, we need to specify. We need to have the like a basic information, like a CO2 emission factor for the natural gas or like a fuel oil. So for the primary energy, we need to know about CO2 emission factor or like a pricing for the tariff for the primary energy, and also like a operation safety rule or like fuel cost, and also like equipment operation range, and so on. Yeah. And then this part is the like optimization part. So So since this is optimization, we should have the objective function. So objective function will be can decided by customer side. So for example, some customer focusing on like cost minimization. Some customer may focusing on like CO2 emission reduction minimization. Yeah, and then also in this optimization calculation include all plant model for like a constraint, and then calculate the like optimal set point, and then this optimal set point will be a download into like existing control system. So the Renkei control has some kind of like flexibility. This can be like a totally like online control, or some customer may want to continue the operation of, by operation side. In this case, we can provide the guidance for the reference of the operation. And then also it is important to know the like before after the 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 reduction of the energy by Renkei control. So normally we should set up like an energy management system. So to check like a CO2 emission reduction or like energy efficiency improvement, and also like a monitoring for the each individual equipment. So next slide is showing the step for the Renkei control. So the first step will be a project initiation. So this project initiation is the customer side, like the customer who has a plan needs to considering about the like a boundary of the like a target facility. And also it is necessary to having a review of rough energy saving from like existing data. So that today and tomorrow, the Arjun team will make an explanation of the Excel tool, which provide like a quick calculation for the chance for the energy saving by Renkei control. So during the like short time, maybe consume like 20 minutes or like 1 hour during if you put like a basic information for the air compressor plant or boiler plant, maybe you can estimate like a magnitude of the saving. So then if the size of the saving is like sufficient, it may be good to go into like a detailed feasibility study to ensure the saving amount. Then needs to considering about like a size of the investment, and also each company has a different like philosophy or like a number for the return on investment. And if this like a solution is meet with the company's like a return on investment, we go into like a actual like a system like installation. And then we do at the end of the system installation, we do the commissioning to check the energy saving. So system needs to working correctly and also keep to the work within the like constraint. But also we need to check the size of the saving. That size of the saving is similar with the size of the saving which coming from the feasibility study or not. So if the size of the saving is much smaller than the feasibility study result, we need to like retune our like a system. So then after the important thing is like operational maintenance. This operational maintenance or mainly done by the customer side, the, the 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 company who has like a facility. But this is like a quite important. So basically so this system installation is from like 4 to 6 months. So the installation period and the commissioning period is, if you compare with like hardware, this is like a very short period. So the next slide is like a Renkei control strategy, and so we are always considering about like what kind of strategy is good for this utility plant or this manufacturing process. So we do this kind of like the activity through like a feasibility study or through like implementation. So to having this like a Renkei control strategy, we need to think about like process side. And also, we need to understand about the existing control loop, like which point is like a manipulated variable. We say like set point. and which value we need to monitoring, like a control variable. And then also we need to decide what is our object for this project, cost reduction or profit maximization or like CO2 emission reduction. So to do this, we may need some time like a computer simulation, like a process simulator or like a optimizer, and also it may be necessary for the equipment specification, also plant operation data, or like physical or like chemical like a principle. And then for the like objective needs to consider about a company like objective. Also, of course, to think about this objective, we need to define a boundary. And to understand about like the existing set point or like a monitoring point, we need to understand existing control loop and the measurement point and also operation constraint. So then after this consideration, maybe we can come up with the idea for the strategy for the Renkei control. So the Renkei control strategy, general characteristic, this is a strategy like utilizing the existing control loop. So it is quite difficult to change the existing control loop because this is, in case of the like a grass on like a new plant, it's okay. But so if we try to implement the Renkei control on the top of the existing control system, the plant is already running on the 24-hour like operation. So it is not normally it is not possible to change the like existing control loop. So we are utilizing the existing control loop, but we can set the different set point into the like existing control loop. Also like leveraging the efficiency difference between equipment to improve total efficiency. So we will check the like each individual the equipment like efficiency. So multiple chiller may have each chiller may have different efficiency. The also boiler like air compressor, and then we are trying to like utilizing the better efficient like equipment. But this is like depending on the size of the demand because each individual equipment may have a different capacity. And also the matching with like a demand side and reducing with energy wastage. So this is quite important. We better not to provide like too much utility. But as I told, the manufacturing process side never allow the utility side, the shortage of the utility. So normally utility side to provide the like more utility. So the important thing is like to understand or to monitoring the side of the demand. So if we understand, if we can monitor the side of the demand, we can reduce the utility which needs to provide into the demand side. And also the stabilization operation, for example, like a good like a PID tuning is quite important. Then after we can optimize the operation for the like energy saving. For example, maybe air compressor. So there is a fluctuation for the like discharge pressure, but if we can provide a good tuning to stabilizing like a discharge pressure, we can gradually to reduce the set point for the like discharge pressure. So then this will give us the like energy saving from the like electric consumption by like air compressor. So this is like the example of the Renkei control. So Renkei control is a multi-purpose optimization software. It can be used for the utility plant in many kinds of like industry, food and beverage, chemical plant, car manufacturing, and pulp and paper. And these plants generate on steam electrics for their process. And the district cooling plant for the building or like smart city will be also the target application for the Renkei control. So it can be used as a system to balance between energy supply side and the energy consumption side too. Okay. So this article is about the optimization control for boiler plant for Indonesian like a PT Pertamina in Indonesia. So one of the Renkei control vendor, Azbil, made this implementation. So they have like 9 high pressure boiler for power generation, and these boiler are using like off gas from the plant side, and also fuel oil from the plant side. And we have implemented like a real-time Renkei control system for this plant, and we didn't change any like existing existing system, and we just made like a PID tuning for the existing control loop, and we have download like we have download the like optimal set point like into like the boiler control loop. For example, like a boiler load. So as a result, we could achieve like a best like a boiler load, and we could reduce. This is a quite big, like a 35,000 ton CO2 per year reduction, and and also the like fuel cost reduction is around $3 million US. And also this is like a example for the Renkei control implementation for the district cooling plant in like Singapore Keppel Corporation. And we have implemented like a Renkei control into 3 different like a district cooling plant for the Keppel Corporation, and we could save around like 80% from the total energy for this company. And also this is an example for the air compressor Siam Craft industry in Thailand. And their air compressor system is very complex because they have like a 6 unit of the air compressor, and the age is different, and also manufacturer different, and efficiency is different. So there was a big opportunity for the energy saving by Renkei control. From this plan, we could achieve like around like a 5% saving. This was very successful project as well. So Renkei control has many potential and also very like expandable like a scope, starting from the like a single facility and the multiple facility and all facility in factory, and also sometimes like a multiple company like industrial complex and like a society wide. So this is a summary. So Renkei control is advanced IoT solution concept supporting energy saving and decarbonization. It provides a total optimization by using control technology, and this is a high return on investment, and can decrease energy waste and provide a continuous improvement cycle. And this will be like a quick win solution. Thank you very much for your attention.
Thank you very much, Mr. Mike Suzuki. Will it be okay if you answer 1 or 2 questions, Mr. Mike?
Yes, yes.
Okay. Are there any questions from the participant? Maybe 1 or 2 questions only. Okay. If there is no question, I would like to thank Mr. Mike, right? And I believe after this, it will be Miss Lee's session where she will explain in more detail how Renkei control is applied in boiler and turbine system. And I believe you will have more questions when you see the application of Renkei. Maybe now it's still quite generic, all this explanation. So thank you again, Mr. Mike.
Thank you so much.
So I would like to invite Miss Lee Pyo Ying next to introduce about Renkei control for the BTG system. So over to you, Miss Lee. So for everyone, if you have any question, you can raise up your hand using the raise up hand function at WebEx, or you can also type your question in the chat box. Yeah, and we'll ask the question after the presenter have complete their presentation. Mr. Mike, you can unshare your screen.
Yep, I'm trying to do that, but I cannot find the control panel yet.
Okay, thank you.
Pio-san, Pio-san, can you override? Oh, now I
Yeah,
see.
it's okay now. Miss Lee, we cannot hear you. We cannot hear you, Miss Lee.
Hear me now?
Yeah, okay, we can hear you now.
So is the screen still shared?
Yeah, still maybe you can switch on the slideshow. Yeah, okay, it's fine now. Thank you.
Okay. Good afternoon, everyone. Good morning. So I'm Renkei from Data. Also working with
Your mic is not so clear, Miss Lee.
not so clear.
Yeah, it's breaking.
Is it slightly better now?
No, it's not. It's not okay on my side. How about the others? Yeah, give Miss Lee a few minutes. Yeah.
Okay. Good afternoon. Good morning. So
Yeah. Okay, it's better now.
yeah, I removed my earphone, but it might capture the environment sound. There's some renovation going on in this building. So sorry for that. So thank you for joining this afternoon for the participants. So I'm Lee Pyo-ying from Data, also working with Aspire Corporation together with Mr. Mike. So I would like to explain about the Renkei control application for BTG system. So basically, the overall content will be like what is the boiler, and then what is the typical control for the boiler, and how do we utilize the typical control to make the operation more effective. So by applying the Renkei control on top of the existing control system. Then we will explain from boiler and then to the turbine. So first is the boiler. So there are typically the boilers like fire tube boiler or water tube boiler. And then what are the differences is that in the boiler there are tubes and shaft for the heat exchanging to make the water to become steam. So the difference is that if this fire tube boiler, then the tubes inside is the gas for heating up. And then if a water tube, then the tube will be containing the water, and vice versa for the shaft. So for fire tube boiler, normally the pressure up to 20 bars, and water tube boiler is more high pressure usage, like up to 100 bars or more, usually in the large power plant. So this is the typical boiler mechanism. So we have let's look at the water tube boiler. So we have these two drums here. First drum is the water, and then the water will go through this tube and go to this steam drum. So this water becomes steam is due to this fuel that firing up and heating up the tube. So the shell is containing this heat, which is like exhaust gas. So the water that becoming the steam will be superheated and become the outlet, or those that haven't successfully become steam, which is like some boiling water will go down from this downcomer and return and going up again. So for a typical boiler mechanism, for the energy balance, normally the energy of fuels, 87% will become the steam, and then the 7% will be the excess gas exhausted and some heat loss due to radiation or the sensible heat of fuel. So when we check the boiler energy efficiency, it's quite important for us to look at from the energy point of view, like how much is the energy input for the fuel and how much is the energy from the steam. So if you get a typical value from 80 to 90%, then your boiler should be fine. If it's less than 80%, then maybe you need to do some maintenance and checkup for your boiler. So these are the boiler efficiency that I mentioned just now. So energy input divided by the energy output. So you can do some calculation for this. So to do this calculation, we need to have the measuring point, because for us to know how to improve our current operation, we need to get their current condition. So to get the current condition, we need to have the measurements. So these are the important measurements that we should have for our boilers. For example, the fuel flow rate, and then we also have the output, the steam flow rate, temperature, and pressure, so that we can get how much of the heat for the steam. And then we have the exhaust gas, temperature, and flow rate, also the flow rate for feed water. Next is about steam turbines. So steam turbine is a machine that have to turn steam to power, as you don't know. So there are typical three type of turbines: condensing turbine, which convert from high pressure steam going through this inlet, expand to a very low pressure steam to be condensed to water. So this one have a more higher power output. And then we have a back pressure steam. So we have the steam go inside and then get out at a lower pressure, but not as low as this condensing turbine. And then we have the one is extracting type turbine, where there are two outputs from this turbine. One input of the high pressure steam. Then we have a extraction outlet here, where maybe from high pressure steam, the steam will be extracted at a medium pressure to be used by the process, and the rest of the steam you continue for the expansion to the very, very low pressure steam to be condensed. So there are three types of turbines usually. Okay. So when we combine the boiler turbines generate, when we combine boiler and turbines, we have this system together. So boilers are the one that's supplying the steam to the turbine for power generation. So this turbine, let's say, is a condensing turbine. So the very low pressure steam is condensed by this condenser, and this water, the condensed water will be recycled back to the feed water pump and become the feed water again to the boiler. So the boiler is using up the fuel together with the air for combustion. Then the water will become high pressure steam again for this mechanism, for this system to be fed to this turbine again. So for BTG, the efficiency, usually we use the heat rate as the calculation. So the heat rate is the total amount of energy required to produce 1 kilowatt of electricity. So the steam flow rate multiplied with the enthalpy of steam minus with the enthalpy of water divided by the power generation. So to do this calculation, so we need to know the condition of the steam. So steam flow rate, temperature, and pressure to get the enthalpy. And then we need to know the power generation. So we need to have these measurements, and then we need to have the feed water condition. So to get the enthalpy of feed water, we need the flow rate, temperature, and pressure as well. So with this information, we can calculate the BTG heat rate. So now this is a typical control loop for the BTG system. So let's say we have 6 boilers, and then they are producing high pressure steam. So this is the input of the field, getting a high pressure steam. So this is a high pressure steam header. And then this high pressure steam is used by the turbines for power generation, also to some other process. So for the power generation, we have 3 turbines here. This turbine, we can say that is a extraction turbine or back pressure turbine, because the steam when inside will become the medium pressure steam. And then we have this another turbine here. It is also extraction turbine from the steam go inside this turbine will become the low pressure steam. And then we have this condensing turbine, because you can see there's a condenser here. So the steam go inside will become water. will not go to this medium pressure header. And then the power generation will go to this power line. So these are the typical controllers. We will look at this controller one by one. Let's focus on the boilers first. So for these boilers, we normally have the flow controller. So this flow controller controls the amount of the fuel. You can see the control valve here based on the amount of the measured flow rate output from the boiler. And then this flow controller is usually cascaded by the master pressure controller. So the master pressure controller will decide the set point for each boilers connecting to this set points of the flow rate, the HPS generation for these boilers, based on the condition of the pressure of this high pressure steam. So the function of this master pressure controller is to ensure the high pressure steam have the sufficient pressure they need for their turbines and also for their downstream process. So usually we don't change the set point for the master pressure controller because it's very important for us to ensure the quality of steam that we need for our process and other usage. So this is normally not, we don't change the master pressure set point. So for typical operation, if everything is controlled by the master pressure controller cascading to the flow controller, then all of the boilers will usually operating at the same load because of the amount of the flow rate is decided by the pressure to fulfill for the user about at the required pressure. So in this condition, regardless of the individual boiler efficiency, all of the boilers are generating the same amount of steam to fulfill the demand. So now we would like to develop the Renkei control strategy for boiler operation. Just now we can see that if everything is the same load, then we are not looking at the efficiency. So in this case, let's say if we already know the boiler efficiency, for example, the efficiency of boiler 1B is better than 2B, is better than 3B. So the boiler 1B is the most efficient boiler, and the boiler 3B is the worst boiler. And then we give them different load instead of the same load. So then which scenario A, there's scenario A and B with the same total demand, total HPS generation. So which of the scenario A and B would give better overall efficiency, like the total fuel consumption will be lesser. So the answer will be very clear, I think. The scenario A will be using the lesser fuel consumption because we are utilizing more of the best efficiency boilers, and then utilize less of the worst efficiency boilers. So even with the same amount of generation, the amount of the fuel consumption will and fix the load for some of the boilers. So let's say we have these 5 boilers and we know that boiler 4 and 5, boiler 4 is the worst boiler and the boiler 5 is the best boiler. Then we can remove them from the cascade, from the pressure controller, and directly give a manual set point for the directly to this flow controller. So we can set the boiler flow to at a lower load as much as possible and set the load for this B5, which is the best efficiency boiler, to highest maximum load as much as possible. And then the rest of the 3 boiler here, which is the intermediate boiler, will continue to be controlled by this master pressure controller. So we can get the operation like these figures that you can see. These B1, B2, B3 are moving at the same load because they are controlled by the pressure controller. They are the kind of the load adjusting boilers that try to fulfill the demand for the user, while these fixed load boilers, B5, will keep at its maximum as much as possible here, and the B4 will be at this lower point as much as possible. Hence, by leveraging the efficiency of these boilers, then we can improve this total efficiency for the whole system. So the energy saving through this location optimization is usually about 5% from our experience. So after we optimize this load allocation for the boilers based on their efficiency, we also can further improve it if we can optimize the number of operating boilers. So this is an additional strategy that we can add on top of the first strategy just now. When the demand is low, maybe we could consider to shut down some of the boilers because it will be more efficient rather than keeping all of the boilers at lower load, because usually boilers are designed to all of the equipments are designed to work best at their rated capacity. So it's usually higher load is better for boilers. So this is a typical operation. Another example. For example, we have these 1, 2, 3. So these 3 boilers are under the master pressure controller. So they are automatically adjusting based on the fluctuation of demand from the master pressure controller. And then we have 3B, 5B, 6B, which are the fixed load boilers. So 5B and 6B are the better efficiency boiler. So this efficiency here defined as a HPS ton per energy input. So the bigger the number is better. So they are fixed at this maximum load, while this 3B, the worst efficiency boiler, is fixed at the minimum load for 3B because it has the worst efficiency. So how do we consider whether we can shut down one of the boiler or not? So we can look at the next page. So to determine the possibility to shut down the number of boiler during the low demand, first we need to calculate the boiler margin. So the general equation is here. Depending on the current number of operating boilers, multiply with the maximum load capacity, that we can minus with this average HPS demand, the total demand. So we want to know whether the current maximum load, how much more excess is the load capacity, while ensuring we can cover the actual average total demand. So for example, we have 6 boiler, and each boiler have the maximum load of 100 ton, and the actual average HPH demand is 480 ton. So if we have 6 boiler, then the maximum steam we can generate is 600. So 6 multiple 100, 600 minus with the total demand 480. So we have some margin of 120. So this margin, boiler margin, is more than the maximum load of one boiler. Means that even if we shut down one boiler, like remove this, then the rest of the 5 boiler is still able to support with this average HPS demand range. So after we know that the boiler margin is sufficient, we need to shut down of the boiler. Definitely, we need to shut down the worst efficiency boiler. So just now we know that 3B is the worst boiler. We shut down it. Then we need to reevaluate our strategy 1. So after the worst efficiency boiler is shut down, then 2B will become the new worst efficiency boiler. So we will make it become the fixed load boiler. So we'll remove it from the master pressure controller cascading and then make it constant minimum load. And then the 5B just now changed from the fixed load boiler to the master boiler because we still need this amount, these 3 boilers for keeping the fluctuation of the demand. So only one 6B boiler is keeping at the maximum load. So now we have one maximum load boiler with the best efficiency and one minimum load boiler with the worst efficiency after shutting down 3B, and 3 boilers for automatically adjusting the load based on the master pressure controller. As a summary, first, we can optimize the load based on efficiency. We need to find out the efficiency of the boiler based on the actual operation data, and then maximize the load for best efficiency boiler, minimize the load for the worst efficiency boiler, and then the rest of the boiler will automatically adjusting the load capacity based on the master pressure controller. When demand is low, then we can consider to reduce the number of operating boilers. So we need to evaluate the boiler margin, whether it is possible to shut down the unnecessary boiler or not. So when we shut down the worst efficiency boiler, then we need to reevaluate the strategy 1 again. So for better image, so this is the existing control system that have the connection to the master pressure control and the flow controller just now. So it is connected to our Renkei control server through OPC, so connection. So for this control server will decide the boiler selection. So it will decide who will be the best boiler, who will be the worst boiler based on the actual operation data. So it will keep calculating the efficiency, and then we'll decide the control mode. So it will after based on the efficiency, it will decide which boilers to be cascade with the master pressure controller and how many boilers is needed to fulfill the fluctuation of demand. And then for those with the fixed load, this Renkei control will decide the load set point for the fixed load boilers, usually to the best efficiency boiler and the worst efficiency boiler. So for this part, and then not only this this function, usually we also will put constraints for the actual operation. For example, we need to have a good balance of the amount of combustion of air. So we do modeling for the air and the fuel ratio to check, to ensure the combustion is efficient or not. So depending on the customer requirement, we can customize the constraint needed for this optimization. So as mentioned just now in the previous section, as we had did the boiler operation optimization in PT Pertamina, Indonesia. So the challenges is that the utility plant that generate the steam for our oil refinery facility is consuming a lot of energy, producing very high CO2 emission. And one of the special characteristic of this utility plant is that the boiler is a dual fuel type boilers, which means that they are not using one type of fuel only. They are mixing the fuel gas and fuel oil for their boiler for combustion. So the challenge is that how do we find the best ratio for the fuel gas and fuel oil? By changing this ratio, the efficiency of the boilers will change. And then the individual mode of a fuel gas or the individual of fuel oil. So there are three different modes, like fuel gas only, fuel oil only, or the mix of the fuel gas or fuel oil, and then we need to determine their ratio. So this is the challenge for this Pertamina plant. So we put our Renkei control system. We optimize the boiler allocation, the one that we explained just now. We also use the operation data to find out the efficiency change when we change the different mode for the fuel type. And then this Renkei control system gives the optimum fuel for the boilers. So it makes the decision. So from this, we have achieved a more stable operation, improved boilers can operate in a higher efficiency condition. Hence, we can reduce some CO2 emissions. As mentioned just now. So if you'd like to read more, you can go to this website. Okay, so now we will move on to the turbine. So after we optimize our boiler already, now the steam will go into the steam turbine for power generation, also for the other lower pressure usage. So in here we have the typical controller, for example, pressure controller. So this pressure controller is used to maintain the medium pressure level for this medium pressure steam header. So it will change the extraction amount based on the fluctuation of this medium pressure steam demand. And then we have the megawatt controller. It's like it will generate the specific number of megawatt depending on your set point. And then we also have frequency controller. So it is used to maintain the power line stability, to maintain the frequency of the power. So this role of this frequency controller is like the master pressure controller. It wants to maintain the quality of the power, like the medium pressure steam, like the pressure controller, maintaining the quality for the steam generation according to the fluctuation of the demand. And the megawatt controller function is like the flow controller, where we can decide the specific amount of generation for the power. Like the flow controller is also can specify the specific generation of flow for the HPS. So there are some similarities just for better understanding. So this is the typical operation. We have this 3 turbine. This is under the pressure controller. So it will automatically adjust based on the steam header condition. And then this second turbine, which is under megawatt controller. So we will automatically, it will be fixed based on the amount of the set point we give to this megawatt controller. And then we have this T3 with the frequency. So this amount will also automatically adjusted based on the voltage for this power line to fulfill the demand. So to do the Renkei control for turbine system, we can, first we need to check the efficiency again. For example, if this T2 is more efficient than T3, then we can set the set point for this megawatt controller higher. Then the turbine under the frequency controller will fluctuate at the lower range here. So they are ensuring the power demand. While for T1, it will adjust the load for the T1, which based on the pressure controller, so we couldn't do anything for the T1. So we will focus on T2 and T3. Like the set point that we set for this T2 will affect the range for this T3 generation. So on the another hand, if the T3 efficiency is found out to be more efficient than T2, then we can set a lower set point for T2. So for example here, then the T3 will fluctuate at the higher load generation depending on the total power demand. So for the strategy one, same as a boiler. First, we want to optimize the load allocation based on efficiency. We want to allocate the load for best efficiency boilers and then minimize the load for the least efficient boiler. And then the rest of the boiler, depending on their controller type, if they are controlled by the frequency controller, then they will have the same load based on the total demand. And when the demand is low, as mentioned, just like the scenario in the boiler, then we can see maybe we could shut down some of the operating steam turbines depending on their efficiency characteristic. So if there's a sufficient boiler margin, then we can shut down, reduce the number of operating steam turbine, and then similar to the boiler, we need to go back to the strategy one to decide which boilers to be connected to the frequency controller, which boiler to be the fixed load, turbine, which turbine will be the fixed load turbine again. This is, I think perhaps I am a little bit too fast for my explanation. If you have any questions, you please ask. This is the end of my slide.
Okay, thank you very much, Ms. Lee. So there are a few questions in the chat, if you are able to answer them, Ms. Lee.
Okay.
So maybe I start with the first question. Okay. So question by Muhammad Adamu has been answered by Mr. Mike. So I think I will skip that. Okay. So the next question is by TS Muhammad Shamsu. So he was asking, create a model is part of Renkei control. May I know what kind of model shows more success in Renkei control?
For the model, usually we use the actual operation data and then do the regressions and then try to, after we have the regression, then we will fit with another set of actual data again to check the accuracy of the regress model. So if there are the error between the model, from the model and the actual operation data become bigger, then we will update the model accordingly to ensure our model is up to the existing conditions. So to keep the efficiency, to keep the efficiency of our, the accuracy of our model.
Okay, thank you. So there's another question by IR Muhammad Imran. So he was asking about why the exhaust pressure from the back pressure turbine is not consistent. So he was asking about the steam turbine.
Exhaust pressure from back pressure of the pressure is the same for the extraction pressure should be the same to maintain the pressure header condition, right? So just that the amount of the extraction is depending on the pressure of the header. For example, currently the pressure is, for example, 5 bar, and then from the sensor, the pressure detected is become, for example, 4.9 bar, and the set point is 5 bar for the pressure that we want to maintain. So if this become 4.9 bar, means that the user side is using much more steam, hence the pressure reduced, right? Lesser steam in the pipeline. So the steam turbine, if the steam turbine is the one that maintaining the master pressure, the medium pressure header 5 bar, you increase the extraction to give more steam to the header. to make it back to 5 bar and fulfill the user side increment of the demand. So I'm not sure, is this answering your question? If you would like to further add on about your question, clarifying something, please, you can open the mic and then we can do the discussion.
Okay, so thank you, Ms. Lee. So the next question is by IR Muhammad Imran. So he was asking, does Renkei comply with IEC 61499 standard?
Actually, I'm not so sure what is the IEC 6199 standard. Could you give me some information about it? About what is the concern by you when you are mentioning about this IEC 614999?
Mr. Imran, are you there? If you can clarify, Ms. Lee. I googled the standard is about control and instrumentation standard just now.
Yep, I'm also
It's
looking.
a standard for distributed automation.
So I think this IEC 61499 will be the existing control system, right? That you, like the DCS for the products for controlling this controller, control valve, and the measurements in the field, while the Renkei control is actually a PC hosting some software. So this software is getting the operation data from the DCS and then do some calculation and then give the set point to the DCS. So I don't think that this Renkei control server have direct relation with this IEC 61499. But then so this is my answer. Hopefully it clears your doubt because we are using the software approach. We are making some programming and then do some calculation for the optimal set point based on the actual operation data.
Okay, thank you, Ms. Lee. And then I think there's one last question by TS Muhammad Shamsul. So he was asking, is the execution for strategy 2 for turbine is similar to strategy 2 for boiler?
Yeah, I think the concept weekday operation change to weekend operation, and then the amount of the average total power demand in the weekend is very low, for example. And then if your maximum capacity 1 megawatt each, and the average weekend generation of power demand, for example, is like 0.8 megawatt, then 2 megawatt minus 0.8 megawatt will be 1.2 megawatt. So 1.2 megawatt is the amount of the excess capacity. So this 1.2 megawatt is bigger than the one of the turbine maximum capacity, for example, the 1 megawatt. So we can consider to shut down the one of the steam turbine, depending on the efficiency. Or actually, it's not as easy as this, because depending on the load of the steam turbine, the characteristic will be different. So we need to look in the detail for the characteristic, then we can decide the better load for each turbine to fulfill the actual demand. But that one is for general feasibility study. Like if you want to consider to shut down, then you can use that simple method. But if you want to have the more precise decision, they need to use from the actual operation data to look at the changes in the efficiency based on the load for the turbine. So in that case, perhaps 2 turbines might be better than one turbine depending on the characteristic curve for the turbine from the operation data. Yeah. Is it okay? Me. Oh. Professor Sharifa, you are mute. And yeah. Mr. Suzuki, Mr. Mike.
Okay, thank you, Miss Lee. Sorry, I
Hi.
lost my connection.
Oh, okay.
Yeah, so I believe all the questions have been answered. So are there any other questions from the participants? Okay, so if not, I would like to thank Miss Lee Pyo Ying for the presentation. So I believe Miss Lee and Mr. Mike have to catch a flight in a moment. So thank
Yeah.
you very much again, Miss Lee and Mr. Mike. So if you have any further question for Miss Lee and Mr. Mike, you can still list it down in the chat and we'll collect all the questions. And Miss Lee will also be here tomorrow to answer all those questions. Yeah. So we'll be taking a short break now. And since we finish early, but we'll still continue at 11:15. Yeah, so you have about 30 minutes for short break. So you can get a coffee, tea, or maybe some tea breaks. Yeah, sorry, we cannot provide it. All right, so we'll be continuing again on 11 at 11:15. Yeah, so I
Thank you
think
so much
that's,
for the questions.
yeah, thank you so much,
See
Miss
you
Lee.
again tomorrow.
Okay, see you again tomorrow, Miss Lee. So for the others, please come back at 11:15. Okay, thank you, everyone.
Thank you. Bye bye.
Hey everyone, we are going to start back the seminar. So for those that would require the STCPD, please switch on your camera throughout the workshop. So I would like to invite our next speaker, which is Miss Azrin. So she will be explaining about the Renkei control assessment tools that have been developed throughout this RTUNE program. And these Renkei assessment tools, you can use it to assess your company or your client Renkei feasibility. Yeah, so it's like the first preliminary assessment before you do all the detailed calculation. Yeah, so with just some base information, you can already predict whether there is a high potential or there is no potential of Renkei control. So if this feasibility assessment form is feasible, then we'll move on to the savings calculation, which require more detailed data. Yeah, like for example, if you're an energy auditor, you may need to audit and gather this data from your client before you can do the energy saving calculation. So the feasibility assessment tool is just a very simple data that you need. All right. So I pass to Ms. Azrin, who will be explaining in more detail about this Renkei control assessment tool, which you can use. Over to you, Azrin.
Okay, Assalamualaikum and very good morning. Thank you, Professor Sharifah. Okay, I will try to share my screen now. Okay. Okay, everyone can see my slide? Okay. So before we begin, I would like to ask all participants to check your inbox because I already sent the invitation link for this Renkei assessment tool in your inbox. Please check both of your personal Gmail and also your work email. Okay, so please let us know whether you receive it or not. Okay, so that later on, after I finish this presentation, we're going to try it together. Okay, okay. Let me start with this. Renkei assessment tool is actually the tool that we developed to assess whether there are high potential or low potential to apply Renkei control strategy. So we already developed for 4 main utility system, which is here as you can see for boiler system, BTG, air compressor and a chiller. So we developed this tool in a Google Sheet platform. If you are familiar with Google Sheet, it's actually like an Excel, but it is online. So it's easy for us to share with you just via a single link. Okay, so I already share with your email, and each of the participant will have a different email, different link, because it is we want to make everyone have the opportunity to try. Okay, so for those who are not received or already received, please let us know in the chat box. Okay, so this is the front page. Okay, the front page of the okay. Okay, so this is the front page of our Renkei assessment tool, whereby we can access via the link from your inbox, and it is online. Okay, you need an internet to access to it. Okay, so this Renkei assessment tool basically have two main parts, input and output. Okay, in simple, I can say input and output. For the input, the user have to key in all the information. We already listened from Mr. Mike and Miss Lee before that all the information, all the data that require. So this tool, this form, okay, is how we're going to convert all the input into this form. Okay, the first main section, which is the input, there are 5 parts. Part 1 will be a general information of a utility system. Later on, I will go, we go through together. Okay, the second part would be the configuration of the utility system. This is the important part for the assessment of the Renkei. Okay, because based on this configuration, we will determine whether the high potential or low potential for Renkei. And then the part 3 would be the equipment specification. Part 4 would be the operation information, and then part 5 would be a control system and data monitoring. Okay, so we develop this form based on certain algorithm and certain criteria to determine whether the Renkei potential is high or not. And then this form will automatically provide the output. Okay, so there is four type of output, which is a preliminary decision, overall analysis result, as you can see here. It will show whether the section, each of the section at your utility system have high or low potential, and it also will calculate the expected fuel saving if we apply this Renkei potential, if we apply this Renkei, and then we'll also calculate the expected CO2 saving. Okay. So, first thing first, it's really important to check the inbox whether you already received or not the invitation. I couldn't see the chat right now. Okay, maybe someone can help. Maybe all the secretariat can help with the uh, anyone have a problem and doesn't receive the invitation. Okay, so the invitation will look like this. Okay, you saw my name, and then you will saw the Renkei assessment tool with a specific ID here. Okay, and then once you open it, hopefully some of you already can open. Okay, when you open it, you will see this. Okay, this will be automatically open at your internet browser. Okay, if you are using Chrome, it will be like here. It will be showing like here, and then you can adjust the scale of this Google Sheet so that it will be smaller or according to your preference. Okay, and then
Hi,
here,
Ka Dream, I'm Hong
yeah,
An. Could
yeah.
you give us 5 minutes because there are quite amount of the participants do not receive the Google form, and then now
Okay,
I will deliver the link to them, and then can you wait for a while, maybe 3 minutes like that, and then
okay,
let us complete sending all the Google link.
okay. Yeah, sure, no problem.
Thank you so much.
Azrin, would it be better if we share the master list and maybe
Sure.
they have received it, but maybe they did not realize where it is?
Okay, I have start sharing first
Mm.
because I
Then we
want to
can share
access
the master list link and then everyone can click the associated
the link. Link.
invitation.
Sure.
And if you still cannot access it, you just request access and we'll provide the access through the email.
Okay, wait for a moment. I'm copying the link to everyone in the chat. Okay. So please access to this link and then access to the link next to your name. Okay, I can see everyone is trying to access the link. From the list of participants now, I can see that the name, the Gmail is quite familiar because last night I did invite it. Try to check on your spam folder too. Okay, some of you, I already received a request. I will approve it. Try to refresh the tab. Okay, make sure you are requesting based on the link at your name, okay? Because we set this Google Sheet to be individual and very specific for each of the participants. Anyone able to access it? Okay, I saw one. Okay. Okay, good. Okay. If that's the case, can we continue?
Okay, if there is any issue, you can put in the chat there. If you still cannot access.
Yes, you can still request. We'll approve it. Okay. So this is because of some of the email are not Gmail account. So when I invite, it could be block. Some of the email already bounced back. Okay. So I'm glad that maybe not everyone, but there are who can already access it. Okay. So if okay to continue.
Yeah, go ahead, Azrin. I think we can
Okay.
continue now.
So when you access the Google Sheet, okay, the Renkei assessment tool or Google Sheet, okay, I like to call it Google Sheet because it is a Google Sheet platform. Okay, so you saw something like this. This is in the front page at a home tab. Okay, this is the scale of I think 75, but it's actually according to your screen. If you have big screen, you can have 100% scale. Okay, so what you need to do while listening to me, you can insert your company contact detail here, and then you can access to another equipment. Because we're going to try the hands-on later on, you can access the equipment by the tab below, or you can access through the link above. Okay, like this. Okay, and then once you key in your information detail will be automatically appear above each of the equipment. So you just need to key in once, and then everything will be automatically appear at each of the equipment. Okay. The next thing would be print. Okay. For those who are not familiar with Google Sheet, this is how we're going to print it later on. If you want to save this as a PDF or save this record or for further action, okay, you can click this symbol, printer symbol, okay, and then you can adjust it and then print it as a PDF. Okay. So we take a look on our first configuration, which is a boiler system. Okay, so this Renkei assessment tool was developed on how to convert this configuration into a form. How do we capture all the information, all the data inside this form inside this Renkei assessment. I think it's very difficult if we say, okay, every participant, please draw your configuration. So we need to prepare another platform. It would be very difficult. So we designed this Renkei assessment tool. Just by clicking all the information, we can capture the configuration. This is the diagram, and then how we from the diagram we convert it into data. Okay. So moving on to our first part would be the first general information of boiler. These are the question. Okay, I believe you can see it if you already access your Google Sheet. Okay, the first would be the utility system. Okay, whether it is a single. The first thing. Okay. As you can see here, the arrow means it is a drop down. And for the empty cell, it is something for you to key in. Okay. So the first question would be a utility system, whether it is a single boiler or multiple boiler. And then this preliminary decision, the form will automatically telling you that you can stop here or you can proceed. Okay. If you choose single boiler, meaning to say you can stop, because this Renkei control have high potential for multiple boiler, not for single boiler. Okay. Then another question would be your load optimization history. You can choose from the drop down list. Okay. The number of boiler you have, the number of steam header you have. Okay. And then the energy or fuel information, the fuel tariff, the type of fuel, okay, and then the CO2 emission factor. Okay, these are the input that you need to key in part 1, and then the form will automatically calculate for you the expected fuel saving and expected CO2 reduction. Okay. The next would be the most important part would be the part 2, configuration of the steam system. Remember just now we have 5 boiler and 1 steam header. Okay, so we capture that information into this part 2, configuration of steam. Okay, you have to select, the first thing is to select the pressure. Okay, select the pressure of the steam header. Okay, you can define it by yourself, whether it is high pressure, medium pressure, or low pressure. Okay, and then for each type of boiler, you can choose the type, whether it is W represent water tube, S represent smoke tube, T represent small throw boiler, or O that represent other boiler. Okay, so this type of boiler will determine whether the Renkei potential is high or no. Okay, and then the connection between the header, you can select which header are connected to which header, and then the connection mode, cascade to cascade to master pressure control or not. I believe Miss Lee already explained how this master pressure control is done. Again, there will be another decision here, okay, that showing whether it is a high potential or low potential for Renkei, automatically showing that based on your input. And then if you have this high Renkei potential, you can proceed to part 3, part 4, and 5. But if there is low potential, you can stop there. Okay. I think I have to move faster because we're going to have a hands-on. Okay. For the part 3 would be the type of fuel for each of the boiler, whether it is a fuel oil, fuel gas, or biomass. So you can choose from this drop down. Okay. You can choose from this drop down each of the boiler. The installation year, 2003, 2020, and then the steam capacity in a ton per hour that you have to key in at each of the boiler. Okay. The next would be part 4, the operation information. Okay. For each of the boiler, the status of the operation, whether it is a running, a hot standby, or stopping. Okay. You can choose from the drop down. And then the load percentage of the boiler, whether it is higher than 90%, 80 to 90%, or less than 90%. And another thing what you need is you need to key in the total demand for the steam header. Okay. And then the last part would be on control system and data monitoring. Okay. Okay, for the control system hardware, we just want to know the existing control system at your utility plant utilize what kind of hardware. Okay, this is the list of it. And then for data monitoring and measuring point, there will be two sections where the data is just measured or the data is logged. Okay, the difference between measured and log, I believe when we say measured, it should be in a certain duration of time. And for the measured, if the data only measured, meaning to say there is no just to read, just to measure a real time data, you can just tick here. Okay, but if the data is logged, you have to mention how long it been logged. Okay. So for the boiler system, there are two main data that really require, which is boiler fuel consumption and steam output. Okay. So once you complete everything, okay, before that, the assessment output, okay, this is the formula on how the form is calculating the expected fuel saving. Okay, the fuel tariff time yearly fuel consumption times, we take about 3% saving for each of the this Renkei assessment. This Renkei potential estimate about 3% saving of your fuel and CO2 reduction. Okay, so once you key in everything, it will automatically calculate for you. Okay, to determine whether it is a high or low potential, Jeta already provide us some value, some range of value. If it is higher than 65 ringgit Malaysia, it would be the expected energy saving. Unless for less than 20,000 ringgit, it would be expected to have just a low energy saving. Okay. So this is the hands-on example, but we are not trying. We're not going to try this example. We're going to try the hands-on for BTG. Okay, so this is example. I think you can try by yourself. Once you tried it, you should get this. Your form should looks like this. Okay, with all the information. Okay, so remember that when we have this configuration, okay, how do we translate this configuration inside this form? Okay. Okay. I think it's already more than 50 minutes. Let us try our hands on together. Okay, so BTG plan is about the same as boiler. All the concept, the section, okay, section, each section of the boiler, each section of the Renkei control assessment would be the same. Just we have the turbine. Okay, the concept will be the same. I'm not going to repeat again this because it's just the same as boiler. Okay, just for BTG we have a section for turbine. Okay, we have a section for turbine, and the rest would be just about the same. So let us try together this example. Okay, how do we key in the information when we have this configuration with this data and this data? We try together to key in our own assessment form. Okay, I will stop the slideshow. Okay. Any problem from the participant, or you are already try everything? Okay. The instructor, our Hong An Prof can also view whether the participant already fill in. Okay, I try to make my screen like this so that we can see both slide and the the assessment tool at the same time. Okay. Any feedback from the participant? I don't see anything. Maybe everyone is so exciting to try. Okay. Okay. Or anyone saying something? Okay, no.
Shall we do it step by step? Azrin,
Okay.
maybe you can
Sure.
demo and do it at the same time.
Okay. Okay. So we go to BTG. Okay. Of course, the first thing before you go to BTG, please make sure you insert this company information. Okay, so I will change it to 75 so that it will shows slightly smaller. Okay, just we have just key in your company address, whatever information that we have. Okay, I just put it here what I have. I don't see any feedback from the participant. Are you guys okay? Or you are trying? Or you are leaving me alone to try? Okay, just put any information there. Okay, you can put your information. So we go to BTG. Okay, so all the information will be here. Okay, I see. Okay, thank you. You already fill up that. Okay, we go on to BTG. Okay, this might be small. Okay, okay. First thing first, we take a look on the configuration. Is that okay with this side by side setup? Okay, because I don't want to keep on jumping from slide and Google Sheet. Okay, okay, thank you. Okay, so when we have this configuration, okay, we see this configuration. This is for part 2. Okay, for the part 1, okay, wait, we go for part 1 first. Okay, so here I simplify the information. Okay, I simplify the information. So the first thing that we're going to fill up, which is the type of boiler system. Okay, we have multiple boiler. Okay, so okay, I will make it this smaller so that you can see the changes that I make. Okay, if you choose single boiler, it will shows you a red color. You can stop there. Okay, we have 6 boilers, so we have multiple boiler, and then we have 3 turbine. Okay, we have 3 turbines, so it is multiple turbine. Okay, and then load optimization history. Okay, just we want to know whether you already done it before or not. But don't worry, if you already done it before, just select that or not. Just select any of the answer that you think is okay. And then, okay, I'm going to enlarge it again. Okay, so we have number of boiler 6, and then number of turbine 3, and then number of steam header. Okay, steam header we have 2, which is HPS and MPS. So we have 2 header. Okay, so fuel information. So we are giving a chance to the user to choose more than one fuel if you have more than one fuel. Okay, so the fuel number 1, fuel number 2 if you have, fuel number 3, or you have other than the specified fuel from the list. Okay, we only have here about 3, whether fuel oil, fuel gas, or biomass. If you have other than this, you can you can key in this section. Okay. Okay, then we go. I will choose it is a fuel gas because we use natural gas. Okay, so here comes the table. Okay, fuel gas. We have fuel gas, and then yearly fuel consumption. You can choose to do copy and paste. Okay, or you can type it by yourself. Okay, it's not nice when I copy and paste. Maybe I type it 6067010. Okay, and then the fuel tariff. This is for Malaysia. For non-Malaysia, you can have your own fuel tariff. Okay, but this form I set it to be just this unit. Okay, I'll just limit the unit to MMBTU and the cost in Ringgit Malaysia. I'm sorry for that. That is for simplicity. Okay, so the fuel tariff would be 36.442. Okay, so as you can see here, it's already calculated automatic to you. If you do a Renkei potential, if you do a Renkei for this plant configuration, you will have about 73 ringgit fuel saving. Okay, this is an estimation value, not the actual. You need to go for further analysis. Don't blame me if you don't get this value later on. Okay, this is just an estimation. Okay, for the CO2 emission, okay, we key in the CO2 emission 53.17. So it will calculate automatically. We will have a CO2 reduction about 100 kg per year, 106 kg per year. Okay, again, it's also an estimation. Okay, so we done for the part one. Okay, it says that it's a green. Please proceed to the next. Okay, so we go on for the part two. Okay, the part two, we have 6 boiler. Okay, we go for the boiler section first. Okay, we have the first steam header, which is HPS. So choose H. Okay, and then for each of the boiler, we have here the type. The type is water tube. Okay, so you can choose W for the type of boiler. Okay, this form, we design it to have 6 boiler only. If you have more than 6 boiler, because of this form is designed, this is I can say that it is a prototype. Later on, further development is needed. That's why we limit the number of boiler to 6 now. Okay. Okay, we have a boiler on a HPS header only. Okay, you can just put it as a HPS header, and then you can select connection to a boiler, connection to another header, which is connected to header number 2. Okay, connected to header number 2, meaning to say the outlet from the boiler goes to header number 2, and the header number 2 is medium pressure steam, just like that. Okay, so all the boiler is on the header 1. Okay, from here you already can see on top there is a high, meaning to say high potential to do a Renkei. Okay, and then about the boiler connection mode. Okay, possible to be cascade by master pressure control. As we can see here, all the boiler is connected to master pressure control. So you can choose, you can just tick. Okay, ticks mean yes. Okay, and then for the turbine section, okay, for the turbine section, we have 2 different type of turbine. Okay, I think that would be in the next slide. Okay, this slide, the type of turbine, back pressure and also a condensing turbine. Okay, so we can choose. Okay, so back pressure turbine is an extraction turbine. We put here extraction turbine, 2 extraction turbine and 1 condensing turbine. Okay, so the inlet for the turbine, basically here, basically from HPS. Okay, HPS inlet. So we can choose from header 1. Okay, all the turbine having inlet from header 1. Okay, this header 1. And then the extraction of the turbine, okay, to the header number 2. Header number 2. And then there is none for the condensing turbine. Okay, so just leave it there. So from this configuration, we can see the turbine also have a potential to do a Renkei. Okay. So the controller type for each of the turbine would be a megawatt controller or frequency controller. So we just choose from the drop down. Frequency controller. Okay. So far we already finished part 1 and part 2. It shows that a high potential for Renkei. Okay, so we can proceed to the next section. Okay, the next section is to capture all the information, all the data about the configuration. Okay, so we can continue. Okay, so for simplicity, I assume all the boiler having the same type of fuel. Okay, which is fuel gas. And then the installation year 2008, all is 2008. Okay, so I'm teaching how to key in the data, just like that. Okay, and the capacity are the same. Okay, it could be different depend on your own utility system, but here it just some example for simplicity because we do it online and we want to do it as fast as we can. Okay, so same goes with turbine. Okay, the turbine was installed at 2018 and 2021. Okay, the capacity would be 18.5, 18.5 and 22. Okay, and then okay, and then the operation information. Okay, all the boiler is running. Just click R. Okay, and then the load percentage. The load percentage for boiler is about 80. So you can choose 80 to 90. Okay, and then same goes with turbine. All turbine is running with a load percentage about 50, meaning to say less than 80. Okay, and then we have the I didn't write there the hardware. Okay, we assume it to be as-built hardware for the control system, and then for the data monitoring. Okay, the data is measured. Okay, they measured and log for about 1 month. Okay, put it there. 1 month. Okay, same goes with turbine. Okay, actually it's good to have this data monitoring for the before implement a Renkei. Okay. Okay, we have left something on our right, which is our steam demand. Okay, the steam demand for each of the header would be 1,600 ton per hour, and for the header 2 would be 400. Okay, and then for the electricity demand, it is 35 megawatt. Okay, so I don't know if I quite fast or too slow, or you already finish it. Please respond. Okay, so this is a complete, I can say a complete form of assessment. Okay, so when we have this form with a green color, I would suggest you to contact our Renkei, our team, for further assessment. Okay, so later on you will learn how to do that further assessment. Okay, So far, any question from the participant? Or please tell me you are okay.
Puan,
Yeah.
kalau kita tengok yang untuk boiler and turbine system tu, dia punya fuel is same lah, fuel gas. But
Yeah.
dia punya yearly consumption tu berbeza kan?
We take the overall.
Overall.
For the value here, 67, this is not a correct, of course, not a correct value. I just put that number, but we take the overall fuel consumption, so that we don't have to key in one by one boiler.
No. Because at the on the turbine slide, I have a yearly fuel consumption about 5 million MMBTU.
Okay, I forgot to update actually. It should be the same. Please ignore this slide. Okay, I will remove this table. It's confusing.
Okay.
Okay.
Thank you, Puan. All right.
Okay, thank you. Sorry for that. Okay. Any more question? Oh, I will see the chat. Just too small to key in, yeah. Jadi main-main isi je. Okay. Also can. Just this is a testing. Actually, if you have a big screen, when you enlarge it, you will be large. 100. Okay, you still can see a large because of the screen. This is because this Google Sheet actually just like an Excel. Okay, so the way we do it, I admit that this quite be too small, but it's okay. You just key in to get familiar how to use it. Can you share the number 5? Sure can. Number 5. Okay, I will just share this so that you can see. I think I can enlarge further. Okay, something like this. Okay, for the number 5, it doesn't mention in the slide. I forgot to mention, but we can assume that it have as-built hardware. Okay, and then the data is measured and also logged for 1 month. I believe this data is from the DCS, right? We can have the DCS to record the historian data. Okay. Anything further? I will end about 2 minutes. Okay. Do part 4 have the effect on the assessment? For this time being, no. Okay. Part 5 doesn't have the effect. We doesn't set any algorithm so that it affect. But in reality, okay, because we haven't go through with data, if you already have this data monitoring, it would be much better so that you can monitor your data before you do Renkei and after you do the Renkei. Okay, maybe Prof can add more on that.
Yeah, so
part 5.
basically the reason for part 5 is we want to know if you already have the monitoring system on real time at your plant. Yeah. So for example, are you currently monitoring your steam flow rate currently? Because if you don't have the steam flow meter, then the cost to install the steam flow meter will increase, of course, will increase the investment cost of the Renkei system. But if, for example, you have already a steam flow meter and you have and you are monitoring that data real time, maybe via your DCS system, so that will help make the cost of Renkei cheaper. Yeah, because you don't have to install that steam flow meter. So that's the reason why we need the part 5 information. Basically, we would like to know if you already have existing monitoring and control system. And if you don't have, then the investment cost might be slightly higher because those monitoring system needs to be pre-installed in order for you to do this control via Renkei. Are there any other questions to Azrin? So what Azrin can do is also she can print PDF this all the things that she have key in, and we will share this also in the Google Drive where you download all your notes, and you can refer to that. You can cross check the values from there. Yeah. So I think that's all, and you can still ask question in the chat while we are going through the next session to Azrin. Okay, so I think thank you very much, Azrin. I think we can move
Okay,
on
thank
to
you.
Fakroni next. Thank you. Okay, for the next session, we would like to invite Dr. Fakroni, who will, okay, so let's say, for example, just now, we have done the feasibility analysis for the BTG system, yeah? So from the assessment tool that Azrin have shown you guys, so you have assessed it to be high potential Renkei. So the next thing is you would like to do a more detailed calculation. Let's say you have already collect the data from your client or from your company. So let's say you have already that steam flow rate data, you have that fuel flow rate data from your company or your client company. So the one that Dr. Fakroni will explain next is how do you use that data from your client or from your company to do further calculations, whether there is a potential, what is the potential energy saving for Renkei, right? So this one also, if for example, you're an energy auditor and let's say you put on a portable steam flow meter logger at the site, of course, it's quite expensive. So maybe, for example, you log the data for 1 week or maybe 1 month. So you can use that log data in order for you to do this pre-assessment for your client or for your company, whether this has potential or not. Yeah. So Dr. Fakroni will be sharing a case study where we'll have some data from some client, maybe, for example, or from company A, for example, and then he'll show you how do you process the data. And then from the process data, he'll pass to Hong An, who will be showing you how to use the P graph, yeah, which is a simplified way to do mathematical modeling in a visualization way. Yeah. So I think I pass to Dr. Fakroni now, who will explain about the case study and some pre-processing and analysis of the data that you extracted from a site. Okay, over to you, Dr. Fakroni.
Thank you, Prof. Sarifah. You can hear my voice?
Yeah, we can.
Okay, thank you. Okay, this session is Assalamualaikum warahmatullahi wabarakatuh. This session is talk about the data generation and data processing because our time is limited. So we just use the simple monitoring for 1 day. So actually this part is conduct me and Hong An. This is my part is introduction and simple data generation, how we can calculate the simple model to do the optimization strategy. So I will share the slide presentation. Okay, we want to, before we implement the Renkei control, we want to evaluate that our system is feasible or not to implement the real-time optimization. So to do that, we have to just simple calculation of the simple optimization strategy to know that from the simple optimization, we have saving energy or not. So if we have saving energy for the a couple time, for example, 1 month or 1 day, or it's best is for 1 year, we can calculate the saving so we can make a good decision whether we want to implement the real-time optimization or not. So the first of our study is the background study. The purpose is we want to understanding the operation and optimization goal of the plan. And then we want to, the second step is data gathering. We have to gather the sufficient variable operation data, which will tell the patterns, the characteristics of the plan and operation. After we get the data, we want to analyze. So we want to analyze to grasp the current condition of identity optimization scenario. This means the current condition, we want to calculate our energy cost. We want to calculate our efficient boiler. So, so this is the base case. And to the next step, we want to do optimization, and we want to compare our optimization strategy can be more the lower energy consumption than the base case, the current condition. And then there is simulation. We want to set up the optimization scenario based on our model and simulate the optimization. And for this case, we're using the pgraph because pgraph is very simple tools to optimize our process. And based on the result, our result is here we consider the overall energy saving and CO2 emissions. Okay, to understanding the operation of optimization goal of the plan, the first we gather our data by interviewing our process control engineer or process engineering, and we want to get the map of the process flow diagram so we can see the flow of our stream of our electricity or our energy, and we study existing control loop, which one can be constant loop, on-off loop, or in the adjustable loop. And we getting the equipment specification sheet because with this information sheet, we can calculate the efficiency and we can we can determine the constraint of our utility. Based on this interview and data gathering, we can finding the optimization boundary, the operation constraint. In our case, if we want the constraint equipment operating range, and also the goal of our optimization. Our goal here is minimize the CO2 emission and minimize energy cost. And we can calculate the total of the energy, the current condition. So it is the base case that we want to optimize more. And we know the manipulation point is mean the decision variable. For example, here we want to minimize the energy flow rate, and we calculate the KPI and operation procedures. Okay, for the boiler turbine generation consider here, we have boiler system that can generate the high pressure system, high HPS, high pressure steam, and whether the boiler system, the one part of the steam will fulfill the HPS demand, and another part become the HPS inlet to the turbine. And the turbine, they have two types of the turbines, the back pressure turbines and the condensing turbines. For the back pressure turbine, we can generate MPS and electricity, but for the condensing turbine, we just can generate the electricity. So this is the process flow diagram that we grabs from our plan. Here where we have the 6 boiler, considering 6 boilers, and the manipulated is the fuel flow rate. We can manipulate fuel flow rate. And for the 6 boiler control the pressures, we mean that we want to maintain the quality of the steam. We want generate the high pressure steam outlet from the boilers, and the one part of the boiler, the steam will fulfill the SPS demand, and another part is going to the turbine as the SPS inlet. So if the steam is going down to the turbine, so we have two type of turbine. This is the back pressure turbine, which can generate to the MPS, medium pressure steam, or to the electricity of the power. Here we can see that the condition have the frequency controller that we can adapt the change of the power for the downstream, power changing from the downstream. And the pressure controller, if they have a changing of demand of the MPS, so the control in the turbine can adapt the changing of the MPS demand. So with this process flow diagram, we determine the goal, the constraint, and the condition of our process. The first, our manipulate variable or our decision variable is the fuel gas, and the goal is minimize fuel or energy consumption to reduce the CO2 emissions and to reduce the energy. Whether the SPS, MPS, and electricity become our constraint, become our target. It cannot regulate because it comes from the process. And the second one that we have in the turbine, we have the back pressure turbine to generate the electricity and MPS for downstream. We have to ensure to the MPS balance, and the total SPS inlet to do both of the turbine 1 and 2 must be keep in the certain value, which is the constraint. And also for the electricity, this demand electricity are based on the downstream situation that we cannot freedom to control them because it is the fixed value of for the constraint, and this constraint must be filled. On the boilers and the condensing turbine condition, we want that all 6 boiler is in the master pressure controller. The number of boilers connecting to the master pressure controller can be manipulated, depend on the fluctuation of the SPS demand. And for the condensing turbine, condensing turbine with a frequency controller, the load will be adjusted automatically based on the power demand from downstream. So here we want to decrease the amount of fuel gas, but we want to attain the fixed value of the SPS demand, MPS demand, and electricity demand. So the overall fuel gas consumption can be reduced by back pressure turbine load allocation optimization. And the second one is boiler load allocation optimization. Okay, this from the information of our data, we can formulate the problem optimization that we will simulate for the big graph. So for the load allocation optimization, our objective is to minimize the fuel consumption. The strategy that we want to maximize the load for the best efficiency boiler, we put the minimum load for the least efficient boiler. And we equally distribute the rest of the load as boiler with the master pressure controller. The manipulation variable is the SPS load in the boilers. The responding variable is the fuel gas flow rate. And we specify the constraint. Our constraint is the maximum SPS load for each boiler, which is in our case is 480 tons SPS ton, and minimum SPS load for each boiler is 240 ton SPS per ton. Whether for the back pressure turbine load allocation optimization, we have the objective of our strategy is to increase the power generation in the back pressure turbines, the back pressure turbine group, while ensuring the SPS and MPS balance to reduce the SPS consumption in the condensing turbines. The manipulation variable is the SPS inlet, and the responding variable is the power generation. The strategy is we want to maximize the load for the best efficiency of the back pressure turbines. We put the minimum the load for the least efficiency back pressure turbines. And the constraint that we want to specify is the back pressure maximum power generation, back pressure, the range of the back pressure power generation, which is from the 5 until 18.5 megawatt. And minimum condensing turbine power generation is 11 megawatt. And we want to ensure that total power generation from the turbine 1, turbine 2, and 3 is not changed. We will fix it, and will be changed based on the demand. And we want to ensure that SPS and MPS in balance. Okay, after we have the optimization strategy and optimization formulation of the objective function and constraint, the first here, we want to develop the model. So to develop the model to be optimized, the first you want to do the data gathering. The purpose is we gather sufficient reliable operation data which would tell the pattern and the characteristic of the plant and operation. The data that could tell us about the operation and plan and equipment of the characteristic. Actually, the good one is minimum is 1 month or at least 1 year data, so we can see the pattern changing in the different season for the the peak season or the low season, so we can see the pattern of it. And after that, because the data sometimes the measurement error or there is a unmatched data, so there will be maybe the weird data or outlier, and you see, so you can filter it to make it a good accuracy. In our system, that we just consider the efficiency of utilities to make it simple as possible. We just calculate the efficiency of the boiler and efficiency of the turbines. So for to filter out, we're using the statistical method. We get a range, minimum and maximum efficiency, or maybe 5% or 10% to get the accuracy of data. We can plot in the regression. We know the R square. If the R square is not satisfied, for example, 95% or 90%, but after we plot it and we do the regression that the result is R square is less than 90%, for example, 80 or something, so we do the data screening. So to develop the model, we have to know because we talk about efficiency, we want to know the correlations. What the data that we require to calculate the efficiency of the boilers, energy efficiency of the back pressure, and energy efficiency of the condensing turbines. Here, the data required to collect is the fuel input of the boilers and amount of SPS generated. Whether for the back pressure turbines, we have to collect the data of the amount of SPS inlet and amount of power generation. And for the condensing turbines, to develop the efficiency model, we need data of amount of SPS inlet and amount of power generation. Next, okay, next, okay. Okay, after we gathering and we know the correlation, the data we want to gather, we want to collect the correlation data that we want to generate the model of efficiency, because efficiency is the simple model that we want to generate to assess the performance of a utility. So we want to analyze the operation of data that we want to know the current condition, and we want to identify the optimization strategies. The for the step is we want to organize the data and to find the pattern. We want to see the pattern is increase or decrease, and how much the range of the SPS or MPS to specify the constraint. And we build equipment a model. So the simple equipment model we consider to this course is efficiency model. We just plot and regression, so we can get the efficiency. And we determine the current overall performance. Here we want to calculate the total energy cost, OPEX, and we want to calculate the total of CO2 emission. Based on that, we want to identify the possible optimization scenario, and we simulate to the P graph. So the data we want to know is we want to grab is the total SPS generation range by all boilers. We will also want the total power generation range by all turbines, and SPS generation trend of the each boiler, and power generation trend of each turbines. So the step 2 is in the build equipment model. The equipment model is used to identify the behavior of the equipment and simulate the behavior of the equipment in the simulation steps. We want to know the change important in parameter due to the variable. For example, our variable is the fuel flow rate, and we want to know the good understanding and knowledge of the equipment characteristic to select the variable for the building models. And for for the step is we can get the very easy tools, only scatter plot and regression analysis. Okay, so the equipment modeling in terms of the efficiency for the boiler, the important the relationship between SPS generation and energy consumption. It means that the y-axis is the HPA generation and the x-axis is energy consumption. So we plot it, we can get the efficiency model. For the back pressure turbine, we relationship is between the power generation and SPS inlet. And for condensing turbine, the relationship between the power generation and SPS inlet. In here, we use it's not use the fuel gas flow rate because some of the fuel is have the different heating value of fuel. For example, we use the fuel gas or oil gas have the different heating value. So we use the energy because maybe the price of fuel, uh, the application or heating or the fuel is quite different. It's not same all the time. It may be different from the batch to batch. Okay, for the step 3 is the of the data analysis. If we want to determine the current overall performance, this means that after we build the model, we know the efficiency, we rank in, so we know the condition of our boiler. For example, for the highest one, it means the boiler is in a good condition. We can run in the highest value of the fuel. For the least or for the lowest efficiency, we run to the minimum one. So we calculate also the total is the most important. The calculation the total one. The total one is very important because we want to compare before and after optimization. It's become the baseline. So in here we calculate the total of the energy cost and the total of CO2 emission. Okay, in our case study, I have explained before, we consider 5 boilers and which is as generate the SPS and for the fulfill the demand process, and we have 2 type of boiler, which is the back pressure boiler for the T1 and T2 and the condensing boiler for the T3. So our data is SPN data, we have MPS and we have power, and we explained before. So for this, we after this, I will go to the exercise to plot it. Actually, this is the example that we can get the profile of the HPS process of the in the under the time. And we just consider only 1 day, 24 hours. So actually, the changing is not too much. So we have the around the total HPS in this process for 1 day is around 1,600 or 1,620. After that, I will plot it to see to show you just to see what the result of the trending and the modeling. The second one, the MS and power demand profile paper process for the 1 day also. For the MPS, total MPS generated from the turbine 1 and second turbine is around 416 and 404. And for the total power to all the turbine is 36.7 or 35 like that. Okay, the second one is we want to analyze the model. Actually, the boiler is based on the gradation analysis between the HPS and energy. Here, if you plot the scatter plot using between the field energy and HPS, we can see the linear regression. We can get the gradient here, 0.3176. It means that for every 1 gigajoule of fuel can generate 0.3766 ton per of HPS. Our efficiency is of the boiler one is 0.376 76 SPS ton per gigajoule. So the efficiency is the gradient of the linear regression. It's very simple model. So we after that we want to ranking, and this is the for the turbine. You see the trend of the turbine. We can plot it after this. For the back pressure turbine, we want the model developed is between the SPS in power and SPS inlet. We can see based on the linear regression, we can see the gradient is 0.0623. This means that for every 1 ton per hour SPS flow rate inlet can generate 0.0632 megawatt per hour. And we ranking to see whether the turbo 1 and turbo 2 is better. From here we can see that turbo number 1 is higher efficiency than the T2. And for the condensing turbine, I want to explain the meaning of our model, and after this I will practice to you how to plot it, how to filter it. Based on the linear regression model, we can see the gradient 0.1497. It means that for every 1 ton per hour FPS flow rate inlet can generate 0.1497 megawatt of power. Okay, I will stop sharing for this slide. I will go to the Excel to see how we plot, scatter, and filtering the data. Okay, next we share about the Excel sheet. Okay, we share it. Tak keluar. Okay. It take a longer time because it's okay. Okay, in the raw data is HPS inlet of the turbines. We have T1, T2 is the turbine of back pressure turbine, and the 3 is the condensing turbine. We have
Fakroni, maybe you can guide them to the Google Drive first. So for
okay.
this Excel, you can go to the Google Drive notes, yeah, and it's under the folder of working session. So in the folder of the working session, there is the BTG Excel template, which you guys can refer to this data that Dr. Fakroni is showing. Yeah?
Okay, you please install the BTG training data and solution. You can install it. So we can run with me. So tell us if you don't cannot access the Excel sheet. So I gave 1 or 2 minutes to you to install or to open the Excel sheet. Okay, I will get the new one.
Okay, for Kronia, can go ahead now?
Okay, so I want to install the new one. Okay, yes, sir. Okay, I will install it. Okay. Okay, thank you for waiting me. Okay, I will share the Excel sheet here. Okay, you can see in the slide of Excel. Okay, our raw data in the turbine is HPS inlet from the turbine number 1, 2, and 3, and the power generation also from the turbine number 1, 2, and 3. And also the information from the boiler, we have information of HPA flow rate in the ton per hour for the boiler 1, 2, 3 until 6, and flue gas flow rate for the boiler 1 to until 6 in the meter cubic per hour, normal meter cubic per hours. Okay, if you want to see the trend, the total of the V1, V2, V5, and V6, for example, we just highlight for the boiler one here, and we insert, and we click in the area chart. We do the stick chart here. We can see the trend of our SPS boiler here. That the total of FPS boiler for 6 boiler is around 2000. It's a simple plot for the trend of the boiler. And for the turbine also, we want to see the total power generation by the turbine 1, 2, and 3. We just simply highlight the column H until J for the turbine. And we insert the plot, the stack plot, and we just click it, a simple one. And we can see the total power generated from the turbine is around 35 megawatt here. This is the time, our recording time is only 5, because we only have 1 day to simplify. Actually, you can get from the 1 month or 1 year is very, very good, because we can capture a whole year or whole month. But for the simplicity, we just consider 1 day. Also, we want to see the accumulation of the SPS inlet for the turbine T1 until T3. We can just simply highlight the turbine T1 and until T3. Okay, we just insert and plot also the same for the stack area. If you can see here that the turbine, all the turbine inlet required for the T1, T2, and 3 is around 490 something. This is from the accumulation trend of our boiler, just for showing. You can see, the information of this, we can set our constraint and set the range that of SPS for each turbine. We can see the minimum and the maximum one. From the data, we can, because a lot of data, we can do the plotting with the from the accumulation was stack plotting, so we can see the trend of our, because it's only 1 day, so it's almost straight line here. Because if you have a 1 year or 1 month, you can see the fluctuation of the data. And we can also get the trend of our SPS to the process generated from the boiler. SPS from the process is as SPS demand. The boiler is going, the one part is going to the process demand, and one part become the SPS line to the turbine. So this is the SPS demand from the process. We can just plot it to see the trend and the insert. Also using this item, but we're using the line. So we can see from this chart the range of our SPS demand is around 1,620 or 1,650. Okay, for the next, you want to see also the trend of the total power to the process is the power demand of the 3 turbines. So we just highlight this column and we insert it to the line, so we can see the trend and the range that we can specify our constraint of the power demand is around 36.7 and 35.4 like that. The last is we want to see the trend of the MPS demand. We just highlight this. It's similar also on the power generation. Just insert and plot using the line. So you can see here. Actually, the trend of MPS, FA, and power demand, we can see, you can, it's very important for us to select the constraint of our MPS demand, our power demand. So will be submitted to our problem optimization formulation. Okay, and from here, we know the current condition of our system based on our data here. We want to calculate the total effects for the raw data before optimization. You can see here, the equation of total effects is the fuel energy is mean that from the total fuel consumed here is in the meter cubic per hours, normal meter cubic per hours. To convert to the energy, we multiply to the 34.79 gigajoule per normal material cubics. So we calculate this from the W10, calculate to this, and calculate to the fuel cost, because fuel cost is because there only one, for example, natural gas. So we click it, and we can see here the plus black cursor. We can click, double click, so we can get the total OPEX here. It's about 289,000. We calculate also the CO2 emission. We have equation is our total fuel also consumed and convert to energy, multiply the 34.79 and multiply to the CO2 emission factor. is 0.05021 ton CO2 per gigajoule, and we enter it here. We have the equation here. I think it's available also in your Excel because I just type it, this equation for you. We just click it on the black cursor twice. So it's automatically, we can get the total of CO2 emission for this row of data. So actually this total cost equation is for before it become base study. And after we do optimization using Renkei, we can see how much the saving or CO2 emission reduction. Okay. And for the boiler, actually just I show to you how to do it. The first, I will delete the filter here. So to see the the real data here. So the first of all, okay, we just delete it. I'm sorry for. First of all, our data only full prorate and SPS. Okay, and then we want to plot between the SPS and fuel energy in gigajoule. So the first of all, we calculate the fuel energy. So by equal to this amount of fuel flow rate and multiply by this value 30 LCV. So we want to constant, we put the dollar between B, okay, and we enter it. Okay. Dollar is not percent. Okay, so we enter it. We can get the value. So we can see there is the black cursors. We click it. So we can, one column is in the gigajoule. So then we plot it and scatter. So we insert the scatter is here. Okay, we're using the data scatter here. So we select the data. For example, this area we remove it. So we add the new one. The X series, the X is our fuel energy. This means this is to be highlighted until the end. Okay, the Y is we delete it first. The Y is our SPS. Okay, we click OK and OK. So we can see that here our system is scattered. So we want to do the linear regression. We click the trend line here in linear. You can see here. And if you want to see the equation, we click the format trend line in linear, and we display the equation and R square. Okay, we have R square is very low, 0.272 something. Okay, and after that we want to filter out to get the 0.9. So I have the range good. So we plot it. So we to filter out, we have to have the information about efficiency per point. So the efficiency is from SPS divided by the fuel energy. Okay, the enter it. we can get the efficiency and we put so we can add some more, can get the more detail in here to add the decimal 3, so we can get the more detail because 0.3 and 0.3 is very not detailed. Okay, after that we highlight this one, we click the data and make it filter it. So we click it, this arrow, and click the number filter. We select the between because okay, before this we okay, I missed one step. Before this we plotted the efficiency. Okay, before the filter rate. Okay, we see this efficiency plot. We can see there is a increase and decrease value. It's not the almost straight line. We want to almost. You can see the trend of our efficiency. Our efficiency is the sum of the point is the upper, sum of the power in the lower one. So we filter it. For example, we highlight and filter this, and we click this arrow. Number filter is between 0.434 until 0.438. Okay, this is our our Titan constraint to filter the outlier data. We click OK. So we can see our R square is improved 0.9 something. Okay, this is our model efficiency 0.3176, and our square is improved from the 0.7 become 0.9 something. So we can do same thing for the B2, B3, B4, and B5. Okay, I will let you to try for the B6. Okay, we go together for the B6. We can get which the blank one. Okay, the first one, we convert the field flow rate to become energy in gigajoule. So we put the equation that the field flow rate multiply by this equation LGV and put in constant value. Okay, well, I hope you can follow me. Yeah. Okay, I just do it in slowly. Okay, after this, okay, you have typing this equation. Okay, we enter it. So there is a equation. If you want to reduce the decimal, you can do home and reduce it. For example, here in the 3 decimal. So after that, you want to get all the data in energy. We can see the black arrow, the black plus here. So we click double. So automatically we can get the value of energy in gigajoule. And then we plot the scatter plot between the SPS to energy. We insert it. We click the chart here, the dot chart. Okay, we appear the dot chart, and the next step, we click the dot chart and we select the data. So remember, we add here. Remember the X value is the energy. So we highlight the energy until here. And the Y value is the SPS. So we highlight the SPS. Okay. And then okay again. So this is the data row that we can get from the chart on the scatter plot. So we want to regression to get the efficiency value. So in this plus, you can click it and tick the trend line. Linear. So from this line, we can select the format trend line to appear our equation and R square. So you can see here, our R square is 0.6, is very not accurate. So how to do it? We plot first our efficiency data for each point. So we calculate here to calculate the efficiency per point. Efficiency equal to the SPS, SPS divide by energy and enter it. And we have the black here. You click double, so we can get all the value here. So you want to reduce the decimal, you can use this. For example, we want to 3 here, 3 decimal. So after that, we plotted the efficiency to see the trend line. Insert using line, as you can see here. So the efficiency, we can sort it from the 0.418 and 0.422 because the range is here and here. We want to get here and here. So we click this to filter it and click the data, click the filter, and click this arrow, this point, and we fill it the number filter is in between. For your information, we can filter from 0.418 to 0.422. Okay, so we can get this. Okay, for the turbine, okay, it's almost the time is almost limited, so I can. So the turbine is very simple, just plot scatter plot, and because the turbine is the data is very good, so the aspect is 0.99 on the turbine 2 also. We just scatter plot between the SPS in the power, SPS become X and power become Y. So on the T3, or we do together. Okay, we do the we insert and scatter. We select the data. The X is the SPS inlet. We highlight the SPS, and the Y data is the power. So okay, so together we click this to get the trend line, and from the trend line we get the format trend line to see the equation and the R square. Okay, we get it. So the turbine is very simple, just scatter because the data is very nice. Okay, from this one, okay, because its time is limited, I will stop this Excel because the time is very limited, just 5 minutes. So I stop it and I share the slide from the presentation. I hope this very is very important, very easy for you because it's only scatter plot and linear regression. I stop it. So I will share my presentation. Okay, based on this one, actually I plot all the six boiler. We can rank our boiler. The first one is the highest one is boiler number 2. The lowest one is boiler number 3. It means that if you have the highest efficiency of boiler number 2, we can operate the boiler 1 to the highest flow rate, the minimum capacity, the maximum capacity. Whether the boiler 3, because the lowest efficiency, we can run in the minimum capacity. This is our optimization strategy. And another one will be adapting. Boiler 1, 6, 5, and 4 will be adapting. We set the load together. On the turbine also, the efficiency turbine number 1 is higher than turbine number 2 for the back pressure. It means that and the back pressure turbine we set in the minimum capacity. And the turbine number 1 will be adapt to the change of the MPS demand. So after we do the calculation of the efficiency, we do the optimization strategy that we want to minimize our energy consumption. Okay, the first one, we start from the turbine, from the bottom to the top. Okay, the line from the bottom to the top. The first, if we adjust the SPS input into T1 and T2 based on the efficiency, we know that condition that the low efficiency obtained in the T2. So we operate fixed to the minimum load. And we set the constraint. The constraint is the MPS generated from the MPS total, which is the generated from the turbine number 1 and turbine number 2. So we want this constraint not evaluated. And we have the constraint of the capacity of our turbine. Turbine number 1, we have minimum and maximum capacity, and turbine number 2 also that. So because we set the minimum of the T2, so we increase the SPS of the number T1 as much as possible, but we not violate the constraint. After that, we calculate the MPS and not violate the MPS constraint, and not violate the ring capacity of the turbine. So we calculate the power generation T1 and T2 after adjustment. It means after operating the minimum load of the T2, and we increase the T1, we calculate the power generation. If the total demand is not fulfilled, so we calculate the power of the turbine number 2. 3 is the condensing turbine, to fulfill the total power generation and HPS consumed by the 2-3. So we check again and ensure that the individual power generation of the T1, T2, and T3 constraint and the total power generation constraint are not violated. And we move to the boiler line. That SPS load for each boiler based on the efficiency to fulfill the new total SPS required after the turbine load allocation. We know that based on the ranking, on the higher efficiency of B3 will set to the maximum load, on the lower efficiency of the B1 set to the minimum load. And we check and ensure that the allocated load within the boiler is within the min-max load of the boiler. And we check also that the SPS total is fulfilled. And we also calculate, this is the final one, all the decrement of the full gas consumption by each boiler after load allocation. We calculated. Actually, this outing strategy will be simulated in the B graph for my friend Mr. Hong An. So this is my part lah, is in the introduction and optimization strategy and generating the model in the simple one. So I think it's enough lah. It's 12. If you have any question, you can type in, and maybe for the next session we can answer it. Or that's it. Thank you.
Thank you, Dr. Fakroni. So I hope everyone can manage to capture So basically, Dr. Fakroni have shown how do you let's say you already have your log data for all your steam, fuel flow rate, the steam inlet, steam outlet from the boiler, as well as going to all the headers. Yeah. So you can calculate the efficiency of each of your boilers, as well as the efficiency of each of your turbine. Yeah. So what we were doing just now is that we have been calculating what are the efficiency for each of the boilers as well as turbines, and we also determine the upper and lower limit where we have a common value, a normal operation value, and we would like to take out any outliers value. Yeah. So later in the afternoon, Hong An will continue and he will show how do you use this efficiency data and put it in the P graph, where from there you can assess whether there is any energy savings potential if you convert your existing control system into Renkei type of control system, right? So if you have any questions, you can type. We will not provide the recorded video, but you have the slides and feel free to ask us if you have any questions in the future. And if you need the solution of the Excel, we'll provide the solution also for the Excel later on so that you can duplicate it. Okay. Right. I think if there is no question, we'll stop here because it's already lunchtime. So we'll continue around 2:30. And if so, please install the pgraph Studio before 2:30. Yeah. So if you have problem with the installation of pgraph Studio, you can come in earlier, maybe around 2:20, and we can try to troubleshoot the pgraph Studio installation on your laptop or computer. But we would like to start using the software already at 2:30. Okay. So I think we'll stop here and we'll continue again 2:30 p.m. So have a nice lunch, and maybe some of you need to go prayer as well. Okay. So thank you so much. And for those that have problem with pgraph installation, please come in earlier at 2:20 p.m. Thank you so much, everyone.
You face any difficulties to install the pgraph, you can type in the chat box there, and then we try to see how we can help you. Thank you. Hi, Mr. Hafizo. Um, if let's say, do you able to install .NET framework? Because in order to use pgraph framework, you need to have the .NET framework as the prerequisite. May I know, do other participants face the same issue too, meaning that you have to install separately .NET able to install pgraph studio directly? If you have the same issue, you can type in the chat.
Assalamualaikum warahmatullahi wabarakatuh and very good afternoon. So we are going to continue the workshop now. Okay, I hope most of you have managed to install the PGraph Studio. Okay, so if you have problem, you can still put in the chat. Okay, and we'll try to help if we can. But of course, if it's the computer problem, then we may not be able to do it. All right. Okay. So I think we can proceed now. Hong An, are you ready? Okay, so just to remind everyone, please switch on your camera if you would like to apply for the ST CPD points. Yeah, we will try to provide if it is approved, right? And in the meantime, while Hong An is presenting, I'll also be putting up the attendance form for the afternoon session. Yeah, so the attendance form for the afternoon session is a different one. So you can please fill it up, the attendance form as well. Okay. So I think I pass to Hong An now. Thank you.
All right. Let me give me a moment. I to share. All right. So I'm Hong An. Okay, good afternoon to all audience. Then I'm Hong An from University Technology Malaysia, and I will start my presentation now. So for those people who cannot, who still face the problem to install PGraph Studio, you can try to deactivate your antivirus software, because some of the PC you have the antivirus software is quite sensitive. So if you deactivate it and then when you try to install, then most of the time you are able to install, because my PC last time also like this. Well, after installation, I turn on again. So most of the time you can able to solve the issue. All right, and then if you have any problems again, you can type in the chat box, and my colleagues will try to assist you. Okay, so I will start the presentation now. So for this slide, they continue from Dr. Fakoni. So basically, Dr. Fakoni just now explained how to derive the equipment model, the performance model for your boilers and turbines based on the log historian data. And then this is the optimization strategy that explained by Dr. Fakoni, and I just elaborate a bit. So basically, you can see there are seven steps here for the optimization strategy. And in short to say is the equipment with lowest efficiency at minimum load. So for example, just now after we deriving the equipment model, we know that T2 is at the lowest efficiency. So later we operate at the minimum load, which is 5 megawatt. And then the B3 has the highest efficiency. So we are set to the maximum load, which is 480 ton per hour. And then the B2 have the lowest efficiency. So we are set them to the minimum load, 240 ton per hour. So this is the summary of this step. And then and also there's an important point to remark here is when we try to met some equipment at the minimum load, we need to ensure the balance boiler and turbine margin is able to cater the overall utility demand. So meaning that the concept is simple. It's basically maybe you can imagine that originally you have 3 engines, and then you use 3 engines to drag some items, and then now you close 1 engine, and then you need to ensure that after you close 1 engine, your engine still able to drag the items. Okay, so then I will explain in deeper in the next later slide after I introduce PCAR first. Okay, so I will go to my presentation now. Okay, so I will briefly introduce what is PGraph and Studio, and then this training slot will take around 30 minutes for me to complete. So in this slide, I will introduce 2 things: the PGraph framework and PGraph Studio interface. So basically, PGraph is a framework, while PGraph Studio interface is the software that embed the PGraph framework. The important lesson here, you will gain insight of PGraph Studio function. So for our case, is used for simulation and optimization of boiler turbine generation case study. And then we also have insight on the PGraph Studio interface. So this is a generalized problem statement. So just imagine that you have multiple boilers at your site, and then you already determine their performance model after energy audit. So you can then do this as what taught by Dr. Fakorni. And then now you want to find the optimum operation strategy to operate multiple boilers to minimize their operation cost. So the information that you have is the process stream. So you know that your input toward boilers is the fuel, and then maybe your fuel is natural gas, biogas, and then you have the products from the multiple boiler steam, boiler which is a steam. So maybe you have different level of steam, and then the intermediate is referred to like high pressure steam generated by boiler, and then before it produce to become before it is stepped down by the turbines. So the high pressure steam is the intermediate, and then your final output is the medium pressure steam. So you also know that amount of your unit operation, you have how many boilers, and you already derive their performance model. So this performance model is like an input-output relationship. So you know that you will use how many energy to produce 1 ton steam or 1 megawatt of power. So beside that, you also collect some data, so you know the operating constraint for your unit operation, and then you also know the fuel price. So now your objective is to find the minimum operating cost, and also you need to know the flow rate of process stream or log of each boiler to minimize the overall operating cost. So so this is a heuristic method to find the optimum solution. So this is the Renkei control strategy proposed by Dr. Fakorni, explained by Dr. Fakorni. Okay, so basically it's same as what I explained in the earlier. So the boiler with higher efficiency, we operate at maximum load, while the lowest efficiency will operate at minimum load. So at the same time, we need to ensure the available capacity of the boiler system after Renkei control can cater the overall utility demand. So in order for us to check this Renkei control strategy, able to provide how many percentage of saving, so we need to simulate the optimization strategy. So one of the solution is you can use the PGraph. Okay, so before you get to know the Renkei control strategy, so if you are the mathematical programming people, so you can also find a solution using the mathematical programming. So basically just now, the performance model that we derive is in the linear formula. So this is a mixed integer linear programming model. And then the example we take as a load optimization or multiple boiler system. So your objective is to minimize the operation cost, and then the decision variables is you can manipulate the steam load toward each boiler. So you can manipulate the steam load of each boiler to minimize the operation cost of boiler system. So the constraint first here is you need to meet the process steam demand. disturb the process after you implement Renkei control. And then beside that, you have to ensure that the steam load of each boiler is within the load constraint within the design capacity of that boiler. So this is the input-output relationship or the performance model that you will derive from the log historian data. And then this is the OPEX equation. So 2.26 is the fuel price. And then your X1, X2, and X3 is the fuel consumption by each boiler. So so if you want to solve like this, you need to have the knowledge to write the optimization model, especially how you need to write in the commercial optimization software. Optimization coding for you to learn, and then you also might need to pay for purchase of software license. So is that so at the same time, actually we are also try to derive to determine the optimum solution based on the MILP model, because just now the multiple boiler system, so the turbine generation system is the MILP model. So is there any tools? So now we introduce P-graph to all of you. So this is the P-graph framework. The P-graph framework is the graph theoretic framework for process synthesis, process network synthesis, developed by Dr. Freder, Liang Tianfen, and co-workers. So P-graph framework is basically like a methodology, the linear programming problem. And the framework itself is embedded inside the P-graph Studio software. So when you want to use the P-graph framework to solve the issue, so you can use this P-graph Studio software, and it's available at this website. So it's free to be used. And also, basically, this software will represent the industrial process in the view of input-output form. So you no need to have the mathematical modeling, you don't need to have the knowledge of how to write the mathematical modeling to simulate the operating strategy, as well as determine the optimal solution of MLP problem. So the P-graph framework is already proven to solve the optimization of all these are some research paper already be published. So this is the example of finding the optimum capacity of combined heat power plant. So it's how to use the P-graph to optimize the abnormal operation. And then this for optimal synthesis of the negative emission poly generation system for reverse osmosis desalination. So today we are used for the boiler turbine generation system, especially for Renkei control strategy. We will use it to simulate the Renkei control strategy, and also at the same time we can also use it to get the optimum solution. So if the participant, if you have any question, you can actually if you want to directly chip in also okay. So or you want to type your question in the chat box also okay. So I'm okay for both. Okay, so just now I already finished the introduction of P-graph framework. So now we will look the software, which is the P-graph interface. Okay, we'll look the interface of P-graph Studio. So when we want map, so first is the steady state operation, and then the process stream have the fixed price. So this process stream can be referred to the raw material, which is the energy input, and then intermediate material and your utility output. The operation for the design case, so the operation unit have the linear capital cost function. So if for the operation case, the operating unit have the linear input output relationship or linear operation cost function. So our case is focused on operation case because the boiler turbine generation system already exists in our industrial site. So we are not going to design. So we are focused on how to input this linear input output relationship into the Pickup Studio. So this is the website, how website looks. And then you can download it via this link. And then the latest version is 5.2.5.0. So this is the Pickup Studio interface. So when you log in into Pickup Studio software, you will look this at the first insight. Okay. So this there are few buttons or the few elements showing at the top of the interface. So basically, this three circle nodes is used to represent the material. So if you have the raw material, you will use the circle, the first circle with the triangle inside. And then if you want to represent your intermediate material, so your node use will be black, totally black one. And then you want to use the node to represent the utility output, so you should use the double circle node. And then this rectangular block is used to represent the operating unit. So the operating unit that we refer here is the boiler and turbine in our case. And then you can use a link to link between this circle and rectangular block. Okay. And then when we want to solve the problems, the algorithm that we use is ABB. Later I will explain in more detail. And then after you in the input output form, so you will use this node to construct your process, and then you will select the algorithm. You put your algorithm as ABB, and then you click run and solve the problem. Then the Pgraph Studio will give you the simulation result. This is just let you to know, okay, what is inside the Pgraph Studio. So later I will explain more detail. So you will learn, you have the hand-on session to how to key in the value. So this is the material node and operating unit that I explained just now. So this rectangular block refer to operating unit, and then this different node represent the different material node, different materials. So you cannot mix up with, you cannot put your raw material using this double circle node. So you will not get the So you can specify the information in each block and nodes. So this is the example how you are going to specify the information in the nodes. So for example, you want to build a node. You want to set up electricity as your material node inside this Pgraph Studio. So when you double click the electricity node, you will come up with these objective properties at your left hand side. So you can specify the name of this node. So in this node, we can set as electricity as it names, and then you is of this material or energy. And then you can also set the constant of flow. So the constant of flow can be represented by required flow and maximum flow. So the required flow is basically like the minimum flow that you need. And then the maximum flow is you don't want to exceed some certain amount for this stream. And then the quantity type, you can actually have a lot of the selection for you to. For this is electricity, but you can also have use mass to represent your materials node. For example, when you select mass, the measurement unit, you can choose ton per hour. So later I will demonstrate, don't worry. So this is an example of operating units. So this is just an example. Maybe we put a CHP module as an operating unit block inside the Pgraph Studio. And then when we click it, and then the left-hand side will show the object properties. And then you can specify name, constraint of capacity. So this time is the within the turn down load and also the maximum design capacity. Okay, so you have the lower and upper bound for this unit operation. And then investment cost in linear formula. If your unit is a new install unit, so you can key in the investment cost here. So if your unit already be established, it's already purchased and built in your site, so you can ignore this investment cost. And then the operating cost, you can also put in the operating cost in linear formula. So linear formula mean that y equal to ms plus c. So the m is the proportional cost toward your capacity of the or the operating load of your unit operation. And then the c is the fixed cost. So you can see here your operating costs have the fixed and proportional. So fixed is meaning that this c, and then the proportional cost is referred to m, right? So when you build the node, you have the operating unit, and also you have also the material node. So you need to connect them together to form a process. So you can click the arrow here and select the link, and then you can connect them together. So now before I demonstrate in Pega Studio, another things I would like to remind here is you can actually set the rate at the link there. So later I will show you how to set the link. So the link is actually you can set it, you can specify the rate to as the input output ratio. Okay, so now I stop sharing the slide first, and then I share the Pega Studio. Okay. Sorry, may I know now my voice, is it clear or still breaking? All right, thank you so much. If let's say my voice is breaking, you can directly on your mic and then ask me to repeat also. Okay. So now I share the pGraph Studio. Okay, so this is the pGraph Studio interface. So as I explained just now inside the slide, right? And then you have you see you can there are different circle nodes, and then also the operating unit here. And then when you click the arrow here, you have the link here. Okay, and then you have the algorithm also here, and also you can click this button to solve the problem. Okay, so for example, if I build example, just example only. Okay, so if you want to use this Pega Studio, so when you want to input the material stream or energy stream, you need to drag and drop. Okay, so you click on it and then you drag and drop on the grid. Okay, so it will show material 1. Okay, so let's say we have 2 material, so I drag another. Okay, and then for example, if maybe I want to represent this as rectangle. Okay, so I have 2 material, and then I have this is like a rectangle. Okay, and then I have a final product, so I can just drag and come here. Okay, so I have to link them together. So this meaning that I use 2 material, these 2 material going into the reactor, and then to form a material tree. So at the same time, I can specify my node information here. So for example, right, and when I click here, you at the left-hand side, you can see the objective properties come out, and then the name I can name it as raw material 1, and then maybe this is in the mass unit, so mass, and then I can put it at a stun. Okay, so I repeat again. So you at this part, you can have a lot of quantity type for you to select to represent your material or energy nodes. So I select mass, and then my unit is stun. Okay, so I click again here. Okay, another thing is I can specify the price. For example, I specify 10 ringgit per ton. Okay, maybe too cheap. Okay, 1,000 per ton. Okay, another one is we go to the next material node. So material 2, I name it as IM2. Okay, and then I create as mass, and again this I create as ton. Okay, so maybe this one is 5,000 per ton. Okay, so the rate here is I use 1 ton and 1 ton of IM2 and 1 ton of 1 ton of IM1 and 1 ton of IM2 to form 1 ton of material 3. Okay, so this one is product. I can name it as product. And mass, and I select again ton. So price I do not specify. Okay, so I just have to specify how many require for. Maybe I need 100 ton. Okay, so this is the operating unit. Okay, so maybe I name it as reactor. Okay, so maybe your operational cost will just simply key in the value. So maybe it's y equal maybe this is 5 and then this is 100. So you can key in the operating cost and then you try to run the solution. So you can actually simulate your reactor how much cost that you need to produce 100 ton per hour for that. So just now we key in the price of IM1, right, and IM2. So in order to produce 100 ton per hour of products, or maybe I should give this, sorry. So this is 2. Okay. So 1 ton plus 1 ton equal to 2. So in order to produce 100 ton per hour of product, you will need to have 50 ton IM2, 50 ton IM1, and then you can direct calculate your total cost here. So your your unit cost for your material, and this is the operation cost for your reactor. All right. So basically, you can actually use this Visual Studio, how you can drag and drop your material node, how you can link them to your operating unit, and then how you can specify the information inside each node. Okay, and then when you're done, you put an algorithm as ABB and you solve the problem. So basically, it now what okay, symmetric meaning that I saw there's some question. Okay, meaning that actually the ratio here you want to specify, you can specify based on your case study. So not necessarily it's symmetry. Maybe you want to this maybe the ratio here 0 0.4, 0 0.6, and then here 1 also okay. It depends on the case study that you face. Okay, not necessarily must be symmetric, not necessarily must be same. Okay, so for example, okay, let me try. Okay, so let me 0.4, maybe this 0.6, and then this one also okay. Okay, so you simulate, then you get the same answer 40, 60, 100. Okay, and then your price total cost will be changed because you have you use different amount of product, right, to produce no, different amount of the raw material to produce the same products. Okay, so now I will go back to the slide again. Where is my slide? Slide. Okay. Okay, now we come back to the slide. Okay, so until now you already know the how basically you have the some understanding of how this Pre-Graph Studio works. Okay, so we go to next slide. So this is example of process representation in P-graph. So for example, this is the reactor, and then this just the things that I demonstrated just now. And then if you have the distillation column, so 2 more, 1 more, 1 more, this ratio is actually you can specify by your own. So not necessarily based on this, based on your case study. Okay, based on your case study, you simulate your process. And then the process is basically in the input output form. So you have the input and material or energy node, and then you will have the output, and then this pass through the operating unit. So you can specify the relationship here. But later I will show how to adapt this knowledge to the boiler and turbine case study. So I will show actually in for boiler, what is it, the representation in the P-graph structure, and also for the turbine. Okay, so don't worry about it. Actually, when you click on the solution algorithm, there are four algorithms here. So there are ADD. To maximum structure generations, SSG is solution structure generation, and then another is SSG LP, right? SSGLP is referred to solution structure generation plus linear programming. And then another one is ABB, accelerated branch and bound algorithm. So in our case, we just use this ABB only. So when you use ABB, you can get the optimal and multiple near optimal structure and solution. So this ABB will solve the your MLP problem quite faster than SSG plus LP. So we will just select this for our like a solver. We will select this as a solver. So shown at the left hand side. Yes. You can check the solve just as I demonstrate just now. You can have you can know actually what is the flow rate of each stream, and then you can also cost of your case study. Okay. So okay. So this is the concluding remarks. So the Playground Studio software can be used to solve MILP problem. So in our case, we will use it to simulate the Renkei control strategy and also do the optimization. And then in Playground Studio, we represent industrial problem in the view of input-output form. So no mathematically modeling language is needed to determine the optimal solution of MILP problem. So you not yet touch about the optimization yet, but later I will Studio can generate the optimal solution, which is important for effective problem analysis and decision support. And then the algorithm that we use is ABB. Okay. More about the pgraph studio, so or application of pgraph in other applications, so you can refer to this reference, so you can refer to this reference to know more. Okay, thank you so much.
Thank you, Hong An. So are we going to the next part?
Okay, me again. Okay, so I will next this session now. Okay.
Okay, so Hong An will
before
continue with the hands-on P graph after this, all right?
yeah, correct. And then do participants have any question before I proceed to next part? Okay, if don't have, I will proceed to next part. So if you have any question, you can always type in the chat. So we also learn together. Okay.
Yeah, they request a 5 minutes break. So maybe we
Okay.
can have a 5 minutes break because we're supposed to start at 3:30, is it? But I think we can have 5 minutes break first. And in the meantime, I think sometimes your voice is breaking. It's like the connection is not so good. I'm not sure if it's your computer or maybe it's the Wi-Fi there. Yeah.
I also not sure because I use the same Wi-Fi as Dr. Fakon just now. Dr. Fakon is actually at my front.
Yeah, but Dr. Fakroni
Maybe
just now was
maybe it's
okay.
my
Not sure.
CC problem.
Okay.
But if let's say my voice breaks me to repeat, I can repeat again, no problem.
Okay.
Okay, there's a question from participants. So what I read out the question. So the question is what are the what are the distinguished features of P graph to the currently available mass balance, energy balance, or economic potential calculation template via MX Excel. Okay, so basically, if you want to simulate the if you want to like simulate the a process, actually you can use the Excel to do it also. So for the simulation, you know the mathematical model of your unit operation, you can actually do it in the Excel. So when your problems become larger, when you have the not only 2 boiler, you have a 6 boiler and total up with the 3 turbines, so your problem become complex. So if you want to find the solution, optimum solution, you can you can use the Pgraph Studio as one of the free optimization software. So for the Excel, you in the Excel, actually there's also the golden mean software is the optimization software also. But when it is encounter with the more complex study like the boiler turbine generation, so it will take a lot of time for you to solve inside the Excel using their software, their solver. So there's for me to what distinguish the feature of Pgraph and Excel is on the optimization. So when and then the solver inside the Excel sometimes take very long time for you to solve it. And then for the simulation, but the reactive, I mean, this is I refer this reactive process as a reaction. Okay, so the reaction, if you know the input output ratio, you can actually simulate inside this Pgraph. But let's say if you want to simulate some very technical relationship, for example, the thermodynamic relationship, the Gibbs energy, maybe I got see some people do that, and then it is okay. Is in terms of the relationship should be linear. If you have the non-linear relationship, the Pgraph structure need am I answering your question? If you have any question, you can write down.
Yeah, I think your voice is still breaking, Hong An. I'm just wondering if we can take 5 minutes break, and then maybe, if possible, can you change computer with acronym maybe? Because if not, it's quite stagger your voice. We cannot hear you.
Now, okay, sure. Now, give me my 5 minutes. I interchange my laptop with Dr. Fakwani. Okay.
Okay, sure. Thank you. So in the meantime, we also have, I think Prof. Raymond is still in. Let me check. Yeah, Prof. Raymond is also inside this chat, inside this WebEx, and he's also he's the expert in Pgraph. Yeah, so we learned about Pgraph also from Prof. Raymond from De La Salle University. So if you have any questions on Pgraph, he can also help to answer. So I think one of the benefit of Pgraph is that it can create a lot of superstructure network. Yeah. So for example, let's say you have a very complex situation, like you have many technologies to choose, or maybe you have many equipments, and then there are several feasible solution. Yeah. So maybe besides the optimal solution, you also have some other possible solutions. So the beauty of Pgraph is that, let's say there are 8 feasible solution. So you can go through each of the feasible solutions. So let's say solution 1, maybe your company decided that this is not, you don't want to do it like this, maybe because of certain constraint of your company. Then you can look at the other feasible solution as well inside the Pgraph. Yeah? So inside the Pgraph, they will list down the feasible solution, starting from the most optimal solution then they also list down the second, third, fourth, and the other feasible solution according to the rank. Yeah. So if you just use Excel, normally you'll only get, for example, one solution, and you cannot play around with the connections, the structure, and so on. Yeah. Prof. Raymond is also here. Maybe if he want, he can also add on.
Thank you, Prof. I think you explained the point quite clearly. I just want to give an example with numbers in it.
Yeah, please, Prof. Raymond.
Using normal optimization algorithms and software, if you use conventional approach, normally you'll get a unique solution, which if it's a global optimum, then it is guaranteed to be the best solution that you can find for your problem. So let's say that for your plant, you set an objective function of maximizing profit, and the solution you get has 1 million ringgit per month. So this is certainly a very good result, but it's very difficult to tell, number one, whether this is the only design that gives you 1 million ringgit per month, because for all we know, there could be other designs that are equally good. But the optimization algorithm stop as soon as it finds a solution that is optimal. The second point Josh also mentioned, let me again explain that with numbers, is in the real world, if your best possible solution is 1 million ringgit per month, in practical terms, I'm sure that a company will be equally interested in inspecting a design whose profit may not be strictly optimal, but let's say it's 999. The practical world, in the real world of engineers, should be worth exploring because it's so near to the mathematical optimum that from an engineering perspective, it might be a good design to work with as well. And with PGRAPH, you can naturally enumerate as many such alternatives as you're willing to inspect. And eventually, of course, Professor Friedler, the original developer of PGRAPH, actually makes this very important point. In the end, it's not the engineer that makes the decision. It's not the software that makes the decision. It's company management. Technical people are able to properly communicate to the decision makers inside the corporate hierarchy so that the company eventually arrives at the best decision. So PGRAPH in that respect is very, very good for decision support. This is all I'll say for now. I believe, I think that explains some of the advantages very clearly. Thank you.
Thank you very much, Prof. Raymond. Okay, I think we can continue now with Hong An, who is going to present in more detail about how to use PGRAPH for the BTG example. So if you are ready, Hong An, we can continue.
Okay, before that, may I know, is it my voice now? Is it clear a bit?
Yeah, it's better.
Better, okay. So if I my voice break again, then Prof, please tell me. Thank you. Okay, so now we have the next training slot, which is talking about how we are going to how we are going to calculate the studio. So let me share the slide in full. So before that, thank you to Prof. Raymond for previously taught us about the P graphs, and then thank you for your explanation. So now I will continue the presentation. Okay. So in this presentation, you will have the tutorial session of how to use the P graph for boiler and turbines case study, and then also you can we will also demonstrate how to use P graph to do the Renkei control for PTG system. And lastly, I will make a conclusion. So the important of the lesson for this training slot are corrected into this P graph structure. So this information is referred to, like, for example, the fuel price, the operating constraint of your utility operation. And then also you will learn how to connect multiple structure of boilers and turbine from a BTG system, and you will get to simulate the operation strategy for the Renkei control of BTG system. Okay. So let's start now. So this is the general structure of utility system that we established for boiler and turbine in the PGraph Studio. So basically, in our case study, and then for example, for this, for example, this is a boiler, and then we will have the energy input, and then we have the operating unit, which is the boiler one, and then we have the utility output as the steam demand. So the in-between structure, which is color one, is the slope intercept structure. So meaning that we will specify the linear performance model of the unit operation at this structure. Okay, so basically you can assume that, okay, is you have the energy input, and then you have the boiler, and then you have the steam demand, and then we in between there's some special structure for you to key the linear performance model. So I will explain this in more detail. Okay, so the slope industrial structure is used to represent the performance model of unit operation or the input-output relationship in the linear formula. So the y is equal to output, x is equal to input, and then m gradient, c constant. So this is actually the linear performance model that is derived by Dr. Falconi in his session to describe the performance of each boiler and turbine. So in next slide, sorry, my PC hang. Okay, so this is an example of representation of boiler in Precast Studio. So we have the fuel input, and then we have the HPS, the steam output. So actually in real situation, we also have the boiler feed water going in, and then we have some blow down water, and then we also produce CO2. But in this case, we just focus on the fuel input and HPS output, because we now are going to minimize the fuel cost by allocating the HPS the steam load on the each boiler based on their efficiency. So this is in the representation of the flow sheet. So we will present in the PGA structure. This will the PGA structure will be like this. So the energy input, operating unit, and then the output. In between, you have the slope intercept structure. So later I will explain how you are going to key in the information inside this slope intercept structure. So next, this is the representation of condensing turbine in PreGraph Studio. So for the condensing turbine, the HPS come in and it produce power. Then at the same time, we have the condensing steam. But this condensing steam is not delivered to the process. So we just ignore it, and then we present the condensing steam turbine in the PreGraph structure like this. So the energy input is a steam, and then this operating unit, which is a condensing turbine, CT, and then your power utility output is the power. So in between, you have the slot intercept structure. So next, this is the representation of back pressure turbine in Precast Studio. So for the back pressure turbine, we have the HVS come in, and then the HVS is stepped down to the lower pressure level steam, and at the same time it produces power. So you can see here we have the two utility output. So one is the MPS demand, the second one is the power demand. And then we also have a slot intercept structure here to represent their performance model. To input the performance model and other specification into the figure structure. Already explained by Dr. Falconi. For example, the performance model, and then you have the fuel price and also the operation load. So these are the information that is available for this boiler. Okay. In order to simulate this situation inside the Precast Studio, so we have we need to have this structure first. So this structure actually we already built. So the participant actually no need to build one, no need to drag the knot and then drag the blocks one by one. So we already built for you, and then your task is just have to key in the information, and then later it to become a boiler turbine generation. So later there will be the hands-on session. So currently for me, I will demonstrate. Okay. So fuel one. Okay, fuel one, we know the fuel price. So we can key the price here. So the price is at this price per gigajoule. The input-output relationship. So the input-output relationship is 0.4199 x minus 4.6237. So we are keying this value in the link between the B1 and also the pin knot. Then the intercept, since the intercept is a negative value, so we are keying at here. Okay. So this is the when we have the negative constant value, we are keying at this knot. So how we are going to key in is we specify the value at the required flow and maximum flow for this knot. All right. So we are after we specify this in the bigger structure, we already have the we already input the performance model to this structure. And then we know that the operating load of boiler is within this range, so we can specify the value at the capacity, lower bound and upper bound. And then you can try to key in your demand, and then you can get the then you are able to simulate this unit operation inside the PGRaph. So now I demonstrate it in the PGRaph Studio. I stop sharing now. Okay. Let me. Okay. So now you can see my slide or on the PGRaph Studio. All right. Okay. So now I will start show how to simulate it inside the PGRaph Studio. So the information that we have is the fuel price. So the fuel price will be I can let me check. Okay. So okay. All right. So the fuel price already be key in here. So the fuel price is 2.246284 per gigajoule. And then you have the input-output relationship. So it's in the Y equal to MS plus C. So just now, as in the slide, you can see is 0.4199 for the gradient. And then for the slope, Y equal to MS plus C, the M is equal to this value. So you can key in the link between B1 and also this pin knot. Okay. And then since the intercept is in the constant value is a negative value, so we will specify at this pin knot. Okay. So just as I say we need to specify the value at the required flow and max flow. All right. Okay. there's a question coming is about time per hour. Okay, yes, time per hour or time per day. Actually, you can set if you want to be time per day, then you can you can actually change the unit here. Change the unit here. So sorry, the graph setting, the problem setting here. Okay, so you can change it. If you want to change into day, then you can specify your time unit here. Okay, so for example, you change into day. So when you drag a new item here, so the unit will represent in the gigajoule per day. Okay, so for example, I just demonstrate to you. So you can see gigajoule per day. Okay, but it will not affect the current unit in the new unit operation install or new not install, then it will be affected by your decision just now. Okay, let me delete. Okay, so just now 0.4199, so we specified our constant here. So when you specify the constant, you just type the value here. You don't need to type the negative, because if you try to type in negative also, you cannot able to key in the negative value. So it will become positive. So this is the constant value. And then we specify the operating range for this boiler. So the operating range is between 240 and 480. Okay. Then after that, let's say we key in some demand. So for example, you want 300 tons per hour. So we try to we use the algorithm ABB, and then we solve the problem. So you can see the maximum structure is here, and then you select the feasible structure one. So you can see if you want to have 300 ton, then you need to have the fuel in this amount. Okay, the 725 gigajoule, and then the price here is this. Okay, maybe I change back. Sorry. So meaning that if I change, it will affect the existing structure also. So I change it to hour. Okay. Yes. Okay. So the total cost for each hour to produce 300 ton is this. Okay. So for example, just now we said that our operating constraint is between 240 to 480, right? And then if let's say you need 500 ton per hour steam. So you try to solve the problem, you will not get a feasible solution, because now the operating the demand is already out of the constraint for this boiler. Okay, so meaning that when you simulate inside the okay, now I go back to the slide. Okay, so sorry, sir. I come back again. Okay, let me share. Okay, so just now we are talking about the negative. How about the positive constant value? So the positive constant value, you will not specify at a constant positive constant value at the pink node here. You will specify at the the orange color, the double circle node here. Okay, the way that you specify also same. You put it as a required flow and the maximum flow as the value of the constant that you get from the performer model. And then the fuel price specification, how you are going to specify your fuel price, the method just now. Okay, so let me demonstrate inside the Pika Studio. Okay, just a moment. So okay, so this is the now we come back to the Pika Studio interface, and then Now we change it. Okay, the fuel price is still same, but now we have the different performance model, right? So the performance model is just now as inside the slide is 0.4055. Okay, and then because it is the positive constant value, we are not specified at this pin node. Okay, so we will delete this. We will put it as 0. Okay, put it as 0 first, and then the positive constant value will specify at this orange color node. So you click it, and then you key in the value. Okay. Okay. So this is the positive constant value. You need to key in for both required and max. And then the operation constraint is still same. So let us run the problem. Sorry, I think I made some mistake. Is this? I have to change back to 300 ton first, because just now we say that 500 ton is out of the operation capacity, right? And then so let's run, and then we get the solution. So when you see maximum solution show here, so meaning that you do not see any no feasible solution message come out. So meaning that this solution is feasible. So you can select feasible structure 1, and then the value of the energy that you need is different from the just now boiler that I simulate in the first example. So just now is 725, right? So now is 739, because they have the different performance model. Okay, so through this kind of the information keying into P-graph structure, so you can simulate the performance of that particular unit operation, regardless it is boiler or turbine. Okay, so I stop sharing, and then so to try to do the example. So this is exercise 1. Okay, you so the participant, you can go to the working material. Okay, you go to a working material file, and then you try to go to the pgraph file. There's a folder which namely pgraph file, and then you try to download the first file, because inside that file they got four. Let me share. So you can go to this. Okay. Okay, so there's a pgraph file here in your working material links, and then when you click in, okay, you can try to download all these 4 files. Okay, so because later you will have the hands-on practice on how to use the pgraph studio software to simulate and optimize the problems. Okay, so you can participant, you can now download all these files. Okay, if you have any issue, you can inform in the chat box. And then after you download it, you have 5 minutes to try to simulate this unit operation. Okay, this unit operation is simple. It's almost similar as what I explained just now. Okay, and then see whether you get the answer or not. Okay, so now participant, you have 5 minutes, and then now and then you can try to log in. Okay, so what you need to do is you key in the fuel price at this node in your performance model at this link, and you need to recognize which node you need to use to represent. Okay, so the answer is here, okay, positive. You need to specify it here, and then you need to set a operation constraint and fix your output demand, and then you check whether you get the same answer or not. Okay, you can start now, and then any problems you can inform me. Okay. Yes, this is the single boiler, because we start from simple example first. We simulate the simple example, the complex until you have the 6 boiler and also 3 turbines. Okay. maybe I share my slide so you can refer and then you can do. Okay, sorry. Okay. Just reminder is before that, just reminder is just now you download the file, right? You try to open that file. After you open and then you use that structure to do this exercise. You are not going to develop this structure one by one, because we already have the customized structure for you, and then what you need to do is you input the information. Okay, and then I show you how to open the file. I show you because I worry some person they don't know how to use. Okay, so basically when you log, you first you need to do is you open your Playgraph Studio software, and then you go to file, and then you open it, and then you want to save, yes, and then yes, then okay, now you can select the file that you want to open. Okay, so just now you download the whole file, right? So you have the file inside your inside your computer. Okay. So you have 2 minutes more. So may I know, is it got any people already get the answer? If you get the answer, can you please type inside the chat box, so at least I know your status? Because this is just the fundamental, and then you need to know the fundamental before I go the case study. I have got the blank sheet, meaning that you cannot download the file, or okay. Okay, what you need to do is okay, may I know, do other people can able to open the file that, and then without meaning that the not the blank sheet when you already, because uh, uh, close this. May I know, do other people, okay, you can open. Okay, so I maybe I show to Mr. Zaini, okay, how to open the okay. Okay, let me you you wait for a while. Okay, so okay. So wait for a minute. I open my Playgraph Studio first. So okay, now I share the my Playgraph Studio file. So basically, when you open it, you you click on the file, and then you need to open the file. You go to the download section, and then just now you already download this file, right? Hands-on single boiler blank, okay? You open it, so you can get the structure. Okay, so meaning that you need to go to file, and then you need to open it from your folder inside the PC, inside your PC. So because time limit, so I just do the example for you, okay? So now for those who haven't complete, so you can see here, okay? So what you need to do is just now I open this file, right? And then your you key in your fuel price, and then your performance model is 0.3176, okay? And then the positive value constant, so you need to specify at this node 93.966, okay, and 93.966, okay. And then you need to specify your constraint at this block, the green color blocks, and then it's 240 for your lower bound and 480 for your upper bound. Okay, so your HPS demand is 300. Okay, so maximum required for is 300. Okay, so now I try to solve the problem so you can get the solution. So the solution here is 648.722 gigajoule per hour, and then your OPEX is represented by here. So you can refer your OPEX here. Okay. Yes. Now I will continue the slide. Okay. So may I know, participant, do you able to simulate? Because I do not get the feedback. Could you please repeat? Okay, I repeat again. I repeat again. So please make a mistake. How do I stop it, correct it, and run it again? I got 0. Oh, okay. A lot of problems. Okay. Let me share again. So I repeat again. So when you get, okay, let's say if you do not get the solution, what you need to do is you for this, okay, wait for a while. Okay, so you click go back to original problem. Okay, it's okay. I try to slow down the progress. Okay, so meaning that if you, let's say you get a not feasible solution, so you need to go back to the original problem and then to change the setting again. If you is at the feasible structure, you cannot change anything. So meaning that you cannot delete, right? And then so what you have to do is you go to original problem and then you change the setting. Okay, so I demonstrate again how you are going to simulate this. Okay, let us do together. So I clear all this value. Okay, I clear all this value first, and then let us start with start from the 0 again. Okay, so what you need to do is okay, so you already open this file. Okay, you already open this file. So you need to go to the price here, and then you specify the fuel price. So what you need to do is click on the fuel node and then price. Okay, price is 2.24 6284. Okay, and then next you need to specify your performance model. So your performance model is 0.4199 x minus 4.6237. Okay, 6237. So meaning that your gradient should be in here, 0.4199. Okay, and then since it is positive slope, So what you need to do is you oh, sorry. The slope is, sorry, I give you the wrong number, 0.3176, okay? 0.3176. And then your constant value, since it is positive number, so you key in 93.966, okay? 0.966, okay? So next, you need to specify your operating constraint for this boiler. So how you are going to limit the operating constraint? You click on this block, the green color block, okay? And then you can see, right, the capacity lower bound and capacity upper bound. So lower bound is 240 and upper bound is 480. Okay, so after you set your fuel price, you set your performance model, and also at this node, and then you specify the operating constraint. Then you can specify your HPS demand. So for example, I need 300 ton per hour steam. So after I specify all this, I solve the problem. So I get the solution. Okay, so how you are going to see the solution? You click on original problem, and then you select feasible structure 1. Then you can see 300 ton per hour, and then you need this amount of gigajoule per hour. And then the total cost is appear here. So the total cost is actually the amount of your fuel use. So you use how many fuel, then you get the total cost here. Okay. Okay, now you got it. Okay, very good. So okay, so let me go to next example. So next example, maybe I show to you because I worry I'm not able to finish. Okay, there's some answer when to use ICF B1 and ICB1. Okay, so in this case, you because this is the structure, and then you will only use this node and this node to represent your constant. When you use this node is when when your constant value is negative. You use this node when the constant value is positive. So the ICFB1, you will not use it. This is just I create it because if I not include this node inside the structure, and then this structure is not visible. So you can imagine it's like a fictitious node. It's a node without function, but it must be inputted in there so I can run this structure. Okay. So now I go to next example, okay? So next example is, I stop sharing and I go to slide, okay? Okay. Okay, so now already done the exercise 1. 2, okay, exercise 2, this I directly demonstrate, okay? So meaning that because the procedure that you key in is actually, so you have the performance model here, okay? Of the condensing turbine that derived by Dr. Fakhoni just now. So this is the same formula used, okay? And then after that, you this is the operating constraint of the condensing turbine. And this information is get from Dr. Fakhoni's side is between 11 megawatt and 22 megawatt. So now you need to you have the demand which is 20 megawatt per hour. So now we try to simulate inside the playground. So I just demonstrate and then because of the time constraint, okay? So let me share. Okay, so I open my file first, wait for a minute. Okay, so combine content, combine content. Okay. Okay, so now I share the okay, now I have the HPS come in and then you produce the power. So this is the condensing turbine operating unit. So as I say just now, the performance model, you have to specify your performance model because at this case we do not specify the price of HPS because the price of HPS will determined by boiler. So just now we know that just now when we type in 300 ton per hour, then we know the price. Okay, so we already calculate the price at the boiler side. So the HPS, we don't need to key in any price here. Okay, so 0 4197. Okay. Then it is the positive constant value. So we will key in require for 6.425 and 425 and 6.425. Okay. And then now you already specified the perform model. Then it is operating within 11 to 22 megawatt. Okay. And then your power demand, you can specify it as 20 megawatt. Okay. 20 megawatt. So the procedure is same as what I explained for boiler, and then you can solve the problem. When you click it and then you go to maximum structure, you choose the feasible structure one. And then we know that the ton of HPS required is 90.6814 ton per hour of HPS. So in order to produce this amount of power, you need this amount of HPS. Okay. And then the cost here is 0 because we already calculate the cost at the boilers there. Okay. And then if you want to change anything, you go back to original problem. So you click here, go to original problem, then only you can change the things. Okay. Then only you can amend the value lah. Okay, you can amend the value. Okay. All right. So now we already finish how to simulate for the condensing turbine and boiler. So the third exercise is about the back pressure turbine. Okay, this is a back pressure turbine. So the back pressure turbine is a little bit more step that you need to do, but it's also simple. Okay, the concept is same. So this is the back pressure turbine. So you produce the MPS. Okay, at the same time you produce power. All right, and then the proper model. This is the proper model derived by Dr. Falconi just now. So you have the HPS. So this is a turbine. So just meaning that your input is HPS steam and then your output is power. And then we know that the mass balance, how many HPS come in is equal to your amount of MPS come out. The mass in equal to mass out. So meaning that this stream is 1-to-1. Okay, Z is equal to X, where Z is equal to MPS steam flow, and X is HPS steam flow. Okay, it's simple. It's a mass balance, and then this is the operating constraint given by Dr. Falconi. So my voice break again, is it? Or okay, now do you can hear me? Okay, okay, good. Nice. Okay, so I proceed. So operating constraint of turbine is between 5 megawatt to 18.5 megawatt, and then this is MPS constraint. Okay, so it's 137.74, 351.35. Okay, so the minimum power output demand you need, this is a minimum output. Okay, so it's 15 megawatt, and then the minimum output of MPS is 320 ton per hour. So I will show how you are going to demonstrate to simulate this inside the PGraph Studio. Okay, so basically you have one performer model need to pin at this side because this performer model is referred to HPS steam power. Okay, so this refer to this stream. So you have the performer model here. And then for this stream, it is a performer model which you can just follow the original structure because it's 1-to-1. So you the mass balance. So you no need to do any performer model at this part. And then you need to key in the operating constraint. Okay. So let us demonstrate in way. Before that, just to mention that you inside the PGraph file in the workshop material, you have the 4 file and then 4 files, and then the first file is boiler, second file is condensing turbine, third file is back pressure turbine. Okay, so now we if you want to follow, you need to open the third file. Okay, but now I demonstrate to you directly. Okay, because we are short of time. Okay, so now HPS SAM, we do not specify any fuel price here because we know that the fuel price already calculated at boiler side. If we count again, then we will over calculate the cost. Okay. Okay, and then we need to specify the model here. Okay. So the model is 0. Performer model, okay, 0.632, okay. And then since this time is negative constant value, okay, so we will use the pink knot. Instead of using this knot, we are, sorry, am I sharing the slide now? Sorry, I forgot to share the slide. Okay, so now you can see the slide again. Okay, meaning that I now you can see my Playgraph Studio, right? Okay, so HBS, we no need to specify the HBS knot because the price of HBS, because we already calculate at the boiler side. And then we need to key in the performer model 0.0632 here as the performer model, gradient, the slope, and then we will use the pink color knot to key in the require to key in the negative constant value. Okay, so this is the constant value. Okay, and then we make sure this part you do not key in anything. So supposedly the required flow and max flow is 0, 0. Okay, because it is negative constant value, so we key in at the pink color knot. We do not key in at this orange color knot. Okay. And then we specify the constraint. Again, the same step. So 5 and 18.5 megawatt. Because we know that 1 ton come in HPS work, and then the MPS also 1 ton come out, and then there's no any things that perform model that you will need to set. This is a mass balance, and then you will need to specify the how much operating constraint. Okay, so 137.74, 351.35. Okay, so at this time you have the 2 output, so you will have to so for my case, I just now the minimum power demand is 50 megawatt. Okay, minimum meaning that require flow, so we don't need to specify maximum flow. Okay, the minimum output power demand, we just need to set the value at required flow. Okay, because the demand, right? Okay, so this one minimum, so also we put at the required flow only 320 ton per hour. So this is the data that I show in the slide. So I try to run problems successfully. So go to feasible structure. Okay, so meaning that in order to fulfill 320 ton per hour FPS, you need to have 320 ton per hour HPS. So this is the mass balance. But at the same time, you produce 16 megawatt. Okay, 16.5 megawatt. So just now your minimum is 50 megawatt, right? Because we do not constrain the maximum amount. So the power produced will be more than the process demand. Okay, because at cogeneration is like this, you have the relationship between the heat and power that you produce. Okay, so until now, is it okay? This is just a fundamental. I will at this part, what we do is we just learn how to key in the information into the Playgraph structure. And then the Playgraph structure we already established for boiler and turbine. So what you need to do is you have to key in the information that you collected from the energy audit or from the when you interview the operator or from the process side. Okay, so you key in the fuel price. Okay, and then you know the performance model after you you plot your historian data as shown by Dr. Facconi, and then you know the operating constraint of your unit operation, and then you know the power demand, utility demand. So this information you need to key in inside the Playgraph structure for you to simulate the performance, and then after that you can run the simulation inside the Playgraph Studio. So this is just a simulation. Okay, it's a fundamental. If I not go through this, and later you will be a bit blur how when we go the things go more complex, then you don't know actually how this work. Okay, so we start with fundamental first. So I will now go to the case study. Okay, before this, any question? Any question? Okay, sure. Later, I will after the event, we will send the solution to you, and then you can try. And then if you still have any problems, if you still face the problem, you can contact me later also okay. Okay. So any question? If no, I proceed. Okay, now I proceed to next part is now we want to okay, so this is a bit complex because okay, the model okay is the question coming is the model is dedicated or need to be designed. Okay, actually we design specifically for the BDG system, meaning that if for users you just need to use the same structure to solve the problems. Okay, so you no need to develop starting from the zero and then draw the node link together, all those no need. You need what you if you want to solve do the same things for your site, you can just use the structure that I already we already established structure of boiler and turbine just now to do your case study. So you no need to do by your own. That one is do by researcher. So the user you just can use and adapt the value of your case study inside the established figure structure. All right. So now I come to the second part of this training is about how we can implement the Renkei control strategy of BDG system using P-graph. Okay. So this is a case study presented by Dr. Fakoni. So we have total of 6 boilers, and then we also have the 3 turbines here, and then the two turbine here is the back pressure turbine, and then 1 turbine is condensing turbine. And for each boiler and turbine, we already derived their performance model. And then just now inside the Excel template shown by Dr. Fakoni, you know the HPS and okay, so all the demand is actually stated inside Excel template. So the way later I will show it. So this is a performance model model from Dr. Fakoni. So from the performance model that already plotted, we know that the P2 is at the lowest efficiency. So have a 0.3118 because it had the lowest value of gradient. Okay, and then the highest value of gradient we have put it is the highest the boiler with highest efficiency. So it's 0.4461. Right. And then for the performance model of BDP also same. T1 and T2 is the back pressure turbine, and T3 is the condensing turbine. So within the back pressure turbine, meaning that within the same type of turbine, T1 and T2, we know that the T2 is have the efficiency is lower because it has the lower gradient here compared to T1. So T2 is 0.0552, T1 is 0.0632. Okay, so meaning that from the performance model that we get here, we the based on the Renkei control strategy introduced by Miss Lee and also explained by Dr. Fakoni, we know that we will put B2 at load, and then we operate B3 at the maximum load. Why? Because minimum load we put it as a load because it has the lowest efficiency. And then the boiler with higher efficiency, we operate at maximum load. And others boilers operate equally, meaning that they share load equally to cater the steam demand, okay, steam demand fluctuation. So for the turbine also same, the lowest efficiency I put as a minimum load. So at this part, I do not specify at this as a maximum loads because only have 2 boilers. If I already specify all the load for T1 and T2, and suddenly any demand fluctuation, who are going to cater that MPS demand because only T1 and T2 will produce MPS. T3 is only produce power only. It is condensing turbine. Okay. So this is a HPS demand profile by process. Okay, this is plotted by Dr. Fakoni just now, and also the MPS and power demand profile shown by Dr. Now we are
PDG, the power demand profile, HPS profile, and then we eliminate the outlier. This one explained by Dr. Fakoni, and then we determine the performance model of unit operation. So this one also explained by Dr. Fakoni just now. And then now what you have to do when we want to implement the Renkei control in the PDG. So first step you have to do is you have to download the PGRAPH Studio file for the Renkei control of PDG. So just now, I think most of you already download because that just now inside the PGRAPH folder in the Google Sheet, Google link, they have four files inside the PGRAPH folder. So the last file is PDG, okay, it's PDG. So and then you SEM, if you want to do simulate the things information inside the this PDG file, but I already did do it for you because the thing is same. Your performance model, your fuel price, your operating contract is same as what I explained just now, and then it's totally same. So the PDG file that you get, I already key in all the information for you. I assume that all of you are already able to key in the information. Okay. Then we have to connect the multiple unit operation. Connect the multiple unit operation to form a BTG system, and then connect and simulate the BTG performance based on Renkei control strategy, and simulate the BTG based on hourly load point of HPS and MPS electricity demand, and determine the daily fuel saving and CO2 reduction after Renkei control of BTG inside the simple calculation formula inside Excel file. Okay, so this look a little bit complicated, but no problem. I will explain step by step to you. So look like complicated, but actually when you do, it's not complicated. It's you just link them together only. Okay. So these are the steps how to do for these step 6, 7, 8, 9. If I break into the detail step, this will be a detail step. Okay. So I read through once. Okay, but if you not understand right now, it's okay. Later when I show to you, you will understand clearly inside the figure demonstration. Okay, it's actually simple. Okay, we need to combine the knot from the boiler. Okay, this is a PGRAPH Studio file for Renkei control BTG. So we have so I already built the boiler structure and turbine structure for you based on the amount of the boiler and turbine inside the BTG case study. Okay, so and then I also key in the performance model for you. So the file that you get already completed with all the performance model, the operating constraint, and also the fuel price. A way to key in is similar as I taught just now. So then because we have the 6 boiler and then we have the 3 turbines, we have a lot of the HPS demand node. Actually, all these can be combined together because they are same thing. They are same thing because these are the boiler, and then the boiler, the structure above here is a boiler. So it is a 6 boiler. The structure here is the back pressure turbine. The structure here is a condensing turbine. So meaning that these 6 products are the same. So we just combine them together. So easier to do work. You have a lot of knot, and then you later you also confuse yourself. So we combine them together. We combine all the same knot together. So meaning that this is MPS, this is also MPS, right? And then we can combine the same knot together. So this is power. This is power also. This is also power. So we can combine later. Okay. Later I will show how to combine them. And then, so this I stand by or combine all the HPS knot from the boiler HPS from into a one knot, which namely HPS from boiler, and then we put a HPS simulation. So later I will show it. So we will set B1 at the maximum load, B3 at, okay, sorry, this one is B3 at the maximum load, B2 at the minimum load. I will amend the slide later. So this one B3 at the maximum load, B2 at the minimum load, and steam turbine 2 at the minimum load. So others, which is B1, B4, B5, B6 will share the remaining load equally. So you run again the simulation. So meaning that, simply to say, procedure 1 to 7 is you connect the unit operation to form the BTG. From 1 to 7, from 8, you simulate hourly load of HPS, MPS, and power demand. And then procedure 10 to 11 is you connect them based on the Renkei control strategy. Okay, I know maybe you will feel very confused. You don't know where are you now. But it's okay. I will show you one by one. Okay, so after that, this is almost the end of the training. Okay, I will show how to do it. Okay, don't worry. Let me open the BTG file. Okay. So now I share.
And I suggest you go a bit slower, and then they can follow you. They can do it at the same time while you are doing it.
Okay, sure. Then I have another 30 minutes, half an hour. Okay. Maybe I demonstrate one time, and then okay. Or maybe now you can open your you take your time. I give you 3 minutes, and then you try to open your folder for the BTG. You download the folder first, and then you download the file at file BTG. And then after you download it, you try to open. May I know, do you able to hear my voice now?
Yeah,
Okay,
okay.
all right. And then you try to open the file first. Okay, the fault file, fault file. You just open the keempat, okay, fault file. So after you already open, can you please type some response, and then know, so I can know I can start. Okay, some of the participants already open. Okay, good, nice. Okay, so I try to share my screen. Okay, so when you open the file, you will see like this. Okay, so you will see the things like this. 2, 3, 4, 5, 6 structure like this, and then this represent boilers. Okay, and then you have the two structure like this. So these two structure is back pressure turbines. And then you will have one structure like this. It's a condensing turbine. Okay. And then if you drag a bit, open it, you can actually, you want to make it closer, right? And then you want to see clearly actually what is written. So you can, on your keyboard, you can click the control, click your control button, and then you, at the same time, you scroll your mouse. So you can open big and small, okay? You want to see, you can zoom. Okay, you can zoom by click on control button and scroll your mouse, or you can click on this. Also okay. Then you can zoom, and then you can zoom in and zoom out, and then you can also move. If you want to move, because this structure is a bit very complex, right? And then you want to move. You want to see here. Then what you need to do is you move your cursor, go to the view here at the left bottom side. There's a quick view. Okay, so you can more when you drag, and then the appearance on the grid also morph. Okay. Okay. So let us go slowly. Okay. So now I zoom out. Okay. So you can see this is a field, and then this is a HPS. So this is also HPS. This is also HPS. This is also HPS. So actually we don't need that much of HPS not because all these are same. Okay. All these are same. So what we are going to do is we have to combine these 6 nodes. This 1, 2, 3, 4, 5, 6. We combine it. So how we are going to combine it? We can delete it all. You can select them. You can select them, and then you try to delete. Okay. So participant, are you able to follow? So you can, if you want to try in your Vega Studio, you can try now. So you go to the HPS demand, and then you delete it. Okay. Why we want to delete is because we want to form a new node to combine all the HPS theme together. Okay. I give you 30 seconds. You just go to your file, and then you select them, delete. So after you're done, can you type some response so I know everything going smooth? Okay, good, nice. Okay. So already done, right? And then okay, so at this time we use the intermediate node. Why we use the intermediate node? It's because intermediate node is there's a 3 circle there. The intermediate node is the black color one. Okay, you drag and drop. Okay, so you drag and drop. Okay, so if you want to delete, you just delete anything. Then you click on it, and then you click on delete on your keyboard. Then already click delete. Okay, so why we use the intermediate node, not using the same node as the double circle just now, is because this is the intermediate. So meaning that is the intermediate, because we will produce MPS and power after we step down through the turbine. So this is just the intermediate. So we use the totally black node, and then we can name. Okay, let us name. This is HPS from boiler. Okay. Then your quantity you should put at mass, because this is time per hour. Okay, so time per hour. Okay, in default it will use the per hour unit. So if you do not change anything, the operation will be per hour. Okay, per hour. So now we want to call them together, right? Okay, so you follow me first, later you try on your Pega Studio. Okay, you follow me first, then you see okay, so this arrow you click, and then there's a link there. Click on link. Okay, click on the link there. To the when you come to the operating block, you will this rectangle, see your cursor become like a cross. Okay, so meaning that you can link them to another node. Okay, so for example, I then already done. So meaning that the steam is combined, the boiler is produce the intermediate HPS steam. Okay, so the same thing do for other boilers. Connect them. Okay, so connect them first. Okay. Oops. For Pega Studio. Okay, so if you already done, you can tell me. Okay, so meaning done, just now we delete, we want to combine, so we build intermediate black node, and then we name it as HPS demand. For HPS, HPS from boiler, and then we do not need to specify anything here. We just specify the quantity as a mass, and then the measuring unit is in time, and then we click on the arrow here to do link. Okay, we link the block. Okay, we link the link between the block and node. Is so far okay? Okay, good. Okay. Then then now because this is the boiler system, then in actual they will go to a HPS header first. So we HPS header is a type of we can represent it in the unit lah. So meaning that we drag this rectangular. Okay, well, we drag this, come here. Okay, so we name them, or name it as HPS header. We name at the properties HPS header here. So other thing, we don't need to specify anything because header, we don't have the operating cost, all those. Okay, and then this is already built-in plan. We don't need to have the capital cost. So you just name HPS header, and then now we want to okay, before you going to try on your pGraph Studio, we do one more step more. Okay, so just now we combine this output from all the boiler, right? And then now we want to combine all this together because all this is HPS. Okay, you can see HPS 1, HPS 2, and then HPS 3. Okay, so we combine these three together. Yeah, HPS 3 together. So we delete this, and then you represent also in the intermediate node. Okay, so we put it as HPS from header. We name it as HPS from header, and then we change it into mass and ton per hour. Okay, so I repeat again, what you need to do is you delete all the not here, same stream, and then we can represent by one node only. One node is enough. Okay, so you name it as HPS from header and then change it into mass and unit is done. Okay, so you can do it at your pGraph Studio now. So if you already done, you can click, you can type your response in the chat box. Okay, good. I see some participant done. Okay, let us continue. Okay, so what you are doing now is you do not specify anything. Now you are modify the structure only. You modify the structure based on the logic. Okay, based on the logic sense. You okay. Let us combine all this because they are same things, and then base header, and then now we also follow the logic sense. Okay, think that your boiler already produced a HPS, and then now your HPS will go down and then to go into the steam, right? Go into a steam turbine, okay, or condensing turbine. So this is a logic sense. So meaning that your boiler already produced the steam, and then we want to transport them to the steam turbine. So in real there's a pipeline, but in the pGraph we connect them by a link. Okay, so we just connect them together. 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 Okay. Right. And then let me do something. The MPS demand, we combine them together. Okay. So steam turbine 1 and steam turbine 2, they will step down the HPS steam and then going into MPS. So this is actually same. So we can link them together. Okay. And then for power demand, actually 3 turbine all produce power. So is we can combine them together to make our structure more simple. So else you need to do you will have now after you simply combine them, your structure will be more simple. Okay, so now you can do in your pGraph Studio. So what you need to do is you link them together. you transport your steam from boiler going into each turbine. And then the same node you combine together. The power you combine it together, and then the power node you combine together, the MPS node you combine together, okay, to become one, each one. Okay, now you try to do at your Pika Studio. So after you're already done, you give me a response. Okay, wow, for so fast. Okay, good. Then you're already familiar with Pika Studio. Okay, very good. Okay, now so now you see okay, now you see maybe we another 15 seconds. So we wait for other participants. Okay. Okay, so now you already combine the node. Okay, let's go back. Just now the slide, you see that there's the HBS demand. You have the HBS will be delivered to downstream, and then you have the MPS will be delivered to downstream, and also power will be delivered to process. So now you can see your product is only HBS and power. So you need to have a new product node to represent HBS. Oh, why? Okay, you need to do another node for HBS. So maybe you will ask, why you don't use this node only? Because in pgraph you cannot your product if you already specified product, and then when you link again to the another operating unit, it will like have some problems. So to make it simple, okay, to make it simple, also by logic sense, you can actually get the steam from here. Is it? You can deliver the steam to the process from this node, because this is the steam from the HBS header. Okay, so let me demonstrate. Okay, this is a little bit different. Okay, so you drag a node, the product node here. This is a final product. So you drag a final block there, and then you name it as HBS demand. So this HBS will be delivered to the process. Okay, so this is air mass and this time per hour. Okay, my time per hour. Okay, time per hour. And then this unit we drag a red block. This one is a black block, a black rectangular box. Okay, the operating unit. This is just a fictitious. Okay, fictitious meaning that we must put in. It don't have any you actually in real you don't have this unit, but you put in so you can run the Pika Studio smoothly. Okay, you can run the Pika Studio successfully. So this unit you can name it as anything. Okay, then I will tell you why you need to put this. Okay, so let me see is distribution. Okay, so this distribution. Okay, distribution. So you connect them. Why you need to have this new operating unit, and then this operating unit is actually do not exist on site. Why you have to key in is you cannot link two material not together. Let me try. Okay, yeah, I show you, you cannot do this. You will not get the link between two material nodes. So what you need to do is you pass through one unit operation, which is fictitious one. In real, we don't have this, but in order to run the Pika smoothly, we build a new unit here. Okay, so this unit we no need to specify anything. We just need to name it, and then we no need to specify the capital cost, all this, because in real we don't have this unit. This unit is add in is because we want run the simulation smoothly. Okay. Okay, now you can try. Okay, so we are almost come to the end. Okay, so you already done your PTG structure. Okay, now you try go to your Pika Studio. What you need to do is you try to input a HBS demand node here, and this node is using the double circle node. So why you need to have this? Because this is the demand sent to the process. So this is also recognized as one of the output demand. And logic sense, we can get the steam from here. So we just connect them. In between, we need fictitious unit. Fictitious unit in this unit doesn't have the meaning or doesn't have the not exist in real, but we put it because we just want to run the simulation. Okay, you try first. Okay, take your time. Take your time. If you're already done, you can key in the chat box. Okay, so I know your status. Okay. Wow. Okay. Okay. We wait another 20 seconds. Okay. Then so just for your information, at this stage you already done all your thing. You already do something you already construct your BTG system inside the pgraph studio. You already done everything. Okay. So what you need to do is, okay, how we decide if we need fictitious unit? Okay, this is a good question. Okay, basically, as I just now explained, when you want to connect some nodes between the material node, okay, you cannot connect them together. You cannot connect them together. So what you can do is you input a fictitious node, fictitious operating unit here to enable the link between these nodes. So in order to answer your question is how you want to know you want to have a fictitious unit. One of the case is if you want to link between two material nodes, you need to have a fictitious unit. Okay. So until this stage, okay, or you already have 6 boiler, and then this 6 boiler produce HPS steam going into a HPS header, and from this HPS header, you this is unit this is the stream. Okay, this is the material. Okay, the HPS from the header. The header coming into the HPS header, and then coming out, and then they distributed to the each turbine, and then going into a fictitious unit to produce the HPS demand. Okay, let us specify our HPS demand. Okay, so I stop sharing. Let us see what is the HPS demand. Okay, the HPS demand you can do Microsoft Excel. Okay, the Excel template that just now you Dr. Fakoni do for the plotting all those. This is the Dr. Fakoni file just now share in his presentation. Okay, so you have the multiple unit here. You have the demand here. Okay, so 405 MPS, 35.6 megawatt, and 1629.7 HPS. Okay, this is the demand. Okay, per hour per hour demand. Okay, hourly utility demand. So I key inside this pgraph. Okay, so I only that I can run the simulation. Okay, so I share again my pgraph studio. So I already jot down the required flow. So let me key in. Okay, the required flow. Okay, 405.71 ton per hour for MPS. Okay, this one is for MPS. Okay, and then for power, you need to do you key in the value. Okay, 35.6 and 35 because almost come to I worry the time not enough. Okay, so meaning that you specified the required flow and maximum flow, meaning that you want this fixed amount of the MPS, this amount of power, and this amount of HPS. Okay, so you specify on, and then you can have the required flow and maximum flow. And until now, you want to simulate the simulation. Okay, so you make sure your algorithm is at ABB. Okay, ABB, and then you try to solve problem. Okay, click on solve problem. Okay, now already solved. Okay, so you can see here you have the feasible structure 1, 2, 3. Okay, so okay, before that, let me check one thing. Sorry, let me check one thing is Sorry for that. Wait for a while. Let me check whether all things is correct or not. Let me stop sharing first. Let me please wait for a while. Let me confirm all the things is correct before I run. Power HPS demand and I run. Please wait for a while. Sorry, I take some time. Confirm all the things is correct. And then better from this check. And then file open. Come in then 457 567.
Hong An, have you connected back the fuel part?
Sorry.
The fuel. Is it already
Oh.
connected into one node?
Yeah. Let me check. So any so actually it can okay, so now I share the solution. Actually, just now these are the just now the things that you get, okay? So just now actually we already get the solution, but the solution it seems like a bit different with what I did before, but it's okay. But at least what you can do is you can actually get the solution, okay? So when just now based on what I already you already do, and then actually you can click on solve problem, so you can get the problem solved here. So you actually you can see maybe I have to okay now you can maybe I move a bit the word here so it do not redundant with the arrow, so you can see more clearly. Okay, so you have your boiler let me confirm again why. Actually, you already get the answer. Just there's some things is things. Okay. Let me explain like this. Okay. The solution is meaning that your boiler 1, boiler 2, and boiler 6 will operate at the minimum load. Okay, and then your boiler 3 and boiler 4 will operate at the maximum load. And what the boiler that counter the fluctuation is countered by boiler. Okay, so you can see the 240 ton per hour, 230 amp per hour, 480 ton per hour, 480 ton per hour, and then also this. Okay, so you can get the solution like this. Okay, and then at the same time you fulfill the MPS demand. Operation cost here. Okay, this 10965.5. Okay, so you can go to the Dr. Facconi Excel file. Okay, you go to the Excel template. I share the Excel template first, right? So now you have the Excel template, and then this is the Excel template given by Dr. Facconi. And then what you can do is you key in the total operation cost just now you get from the P graph. So it's 1095.95 10965.5. Okay, 10965.5. Okay, so now you get you see that your operational cost saving is so meaning that actually you from the P graph what the things, and then after we optimize the load allocation, and then this operation saving, how we get is actually we get we use the total OPEX here, and then this is after Renkei, and before Renkei is this amount. Okay, before Renkei is this amount 1157.25. Okay, and then after you run the simulation you get this result, and then you get the operational saving is you minus the total OPEX before and after. So you use this value minus with this value, and then you will get the operational cost saving. So actually in Excel template, the saving here already show you there's a built-in formula here. Okay, so there's a formula here show you, so you just need to key in and you will get the operation saving. So because the current case study is we have the same natural, we use the same fuel. Okay, then they have the same relationship, because when we operational cost drop, your fuel use is drop, and then your CO2 is drop. So in simple way to say is how many percentage that you get from operational saving, how many amount of saving we can directly convert into CO2 reduction by knowing the how many percentage of total OPEX saving. Okay, so if you, let's say you're saving 5%, then for sure your CO2 emission reduction will be also drop 5%, because it has the same direct relationship. When your cost drop, your fuel consumption drop, and then your CO2 emission reduction. Okay, and then do repeatedly for the MPS demand and HPS demand, and then later I will provide you the file with the solution. So the solution, after you get, if not mistaken, after you already key in all the thing, because this is without keying all this. So after you key in all this, the changes will be power saving is in the median. Later I will show the answer. Okay, so for my part is like this. So before I end my presentation, another slide to go. Sorry, another slide to go is okay, can we combine two HPS from boiler node into one node and remove the HPS header? Will the simulation works? Okay, can we combine two HPS from boiler node into one node? Two HPS node from boiler node. Okay, you mean about this, or let me share, and then this one. You mean you want to meaning that this and remove this, and then you directly combine them together. here, go to here. There's the things that you mean. You want from you want okay, good. Okay, so meaning that okay, if let's say last time I got try before, and then I will suggest you to have input here, okay? Because why is because the in some case when you directly combine, and then meaning that your node here have the multiple input, and then also you have the multiple output. Sometime last time I tried before for this case study is okay, it's no problem. You can directly connect them together. Just why I put HBS header here is because want to like show you where is the header actually. Actually you can do. Last time I tried, if not mistaken, is successful. So you can delete this node and delete this, and then you combine them together. But you don't. But at this way, you are not able to represent your HBS header in the in the pgraph structure. So you want to do it also okay. You want to do it also okay. If because last time when I tried is I think it's okay. So let me let me finish the last slide. Okay, let me finish the last slide. Okay, so make sure that when re-evaluate. Okay, make sure that when you do the Renkei control strategy, your available margins still there. Okay, okay, this thing late tomorrow I will expand. Maybe I take 5 minutes to expand this thing. I will expand tomorrow, but I will make a conclusion here first. So we already learned how to insert the information, which is the fuel price, performance model, and operation constraint and output demand into the boiler and turbine in pgraph studio. And then we know how to connect the multiple boiler and turbines to form a simulate the operation strategy of BTG system in pgraph studio. So we learn how to key in the information, we learn how to connect all the things to form a BTG system by eliminate this node, combine that node, and then we use some fictitious unit. And then lastly, we run the simulation using FV algorithm, and then we successfully get the total OPEX. So you already optimize your system, okay, based on the BTG inside the pgraph studio. So that's all from me. Thank you. Because of my time also, I already exceed the time. Thank you so much.
Thank you very much, Hong An. So I believe Hong An, can you mute your mic? Because it's okay, thank you. Right, so basically, if you have different configuration, yeah, like for example, if your plant have 4 boilers and maybe you have different number of turbines, so basically you can just either delete, or you can, if you have more boilers, for example, you just can copy the whole configuration and you can paste. Yeah, so if you have 7 boilers, you just copy, paste, and add more boilers using the same configuration that Hong An has shown just now. Yeah, so easily by using pgraph, you can draw the actual configuration of your plant or your client plant in terms of the number of boilers, the headers it is connected, as well as the type of turbine, yeah, either back pressure turbine or whether it's a condensing turbine. Okay. And from there, you can do your calculations and get your feasible solution. And as you can see, you do not require any formula, any equation derivation at all by using pgraph. If, for example, you are using some mathematical model, you have to derive all the equations for the boilers and so on. So here you can see that you can easily key in all the information in, out, and pgraph can give you the optimal solution, optimal configuration, and you can play around with the connections and everything. Yeah, so it's an interesting software to do mathematical modeling without knowing how to do model derivations. Yeah. So I think that's all for today. You may not have enough time to try what Hong An has shown just now. So feel free to try it later when you go back. And then let's say you have any questions, you can also ask tomorrow morning. Okay, and we'll be happy to help. So if you want, we can 8:45 to 9. If you have problem with pgraph, we'll have a 15 minutes for us to help answer any questions, help you do your troubleshooting for 15 minutes. And then at 9 a.m., we'll start the air compressor session next. All right. So I think that's all. I think there's another question by Wong. Whoever have question, you can stay back. And whoever doesn't have question, feel free to leave. So thank you very much. And we'll see you all tomorrow at 9 a.m. for the compressor session. And if you have any questions, you can also come earlier 15 minutes to ask us question as well. Right? So thank you very much. And for those that want to ask question, feel free to step back and we'll be happy to answer any of your question. Okay, thank you everyone.
Okay, Wong, maybe I answer you about the feasible structure that you asked is feasible structure 1, 2, and 3. So which one you want to choose is actually we will choose let me show for a while. Let me show my figure structure, sorry. So basically, when you run the simulation, right, as I explained in the previous slide, you can get the optimal and near optimal solution. And then this is the first solution. So for the first solution, you get this value. So this is a 0965.5. And then for second structure, you off one sub boiler, and then the cost become higher. And then this is the third solution. So the cost become higher. So meaning that you use the feasible structure one because the cost will be lower. Meaning that PGraph can give you multiple solution, and then this solution when they are arranged based on the operating the total cost. So the feasible structure one is with the lower cost, and then the structure at the end is with the higher cost. All right. And then thank you everyone. Thank you so much.
So if there's no further question, we'll close the session for today. And tomorrow, feel free to come 15 minutes earlier if you have other questions you want to ask after you have tried some of the case study as well. Okay. Okay. Thank you, everyone. See you tomorrow.